Imagine the open ocean not as a body of water, but as a boundless desert of blue. It stretches out in every conceivable direction, a three-dimensional void where the horizon offers no landmarks, no shelter, and no promise of arrival. To human eyes, this expanse is terrifyingly empty, a continuous, shifting continuum of relentless waves and dark, unfathomable depths. There are no signposts here. There are no trails left in the water to follow, no paths worn into the sea by those who came before. Yet, this featureless space is crisscrossed by invisible highways, ancient and precise routes traveled by one of the most accomplished and enduring navigators our planet has ever produced. Moving steadily through this infinity of blue is the green sea turtle. Watch the way it moves through the water. This is not the frantic, muscle-twitching sprint of a hunted prey, nor is it the explosive, violent ambush of a reef predator. The green sea turtle does not truly swim. It flies. Its body is an absolute triumph of hydrodynamic engineering, sculpted by hundreds of millions of years of evolutionary pressure, not for sudden, erratic bursts of speed, but for unimaginable, unyielding endurance. The broad, smooth dome of its carapace is painted in subtle, mottled shades of olive, amber, and deep brown. The scuts that form it shall fit together in a seamless mosaic that parts the dense medium of water with frictionless grace. Its front flippers are elongated, modified over eons into perfect underwater wings. With each deliberate, sweeping downstroke, these wings generate lift and forward momentum. Cutting through the water with the exact aerodynamic principles a bird uses to cut through the sky. It is a slow, highly rhythmic flight, a measured and confident beating of wings that carries the animal across entire ocean basins and between hemispheres. Every single stroke is calculated to conserve energy, allowing the turtle to glide forward several meters on a single, powerful push. In the vastness of the open ocean, efficiency is the ultimate currency of survival, and the green sea turtle is a master of biological economy. It does not fight the ocean, it yields to it, riding the deep planetary currents to save its strength. But how does it know where it is going? If you were dropped into the middle of the Pacific without a compass, without the stars, surrounded only by a uniform sphere of water, you would be instantly, hopelessly lost. The sea turtle is never lost. It possesses a sensory ability that feels almost like magic to the human mind, yet it is rooted in the deep, unseen physics of our planet. The turtle is, quite literally, tuned into the earth itself. Deep beneath the ocean floor, beneath the crust of the earth, swirling oceans of liquid iron generate a massive magnetic field. This field extends far out into space, wrapping the globe in an invisible shield. But this magnetic field is not perfectly uniform. It varies slightly in intensity and the angle at which it intersects the Earth's surface. Its inclination changes depending on your exact geographic location. The green sea turtle has specialized biological receptors woven into its nervous system that allow it to physically feel these invisible lines of magnetic force. As it glides through the featureless blue desert, the turtle is reading a map written entirely in magnetism. It senses the slight dip of the magnetic field lines. It feels the subtle shifts in magnetic intensity, and it calculates its approximate latitude and longitude with an internal, biological GPS that requires no satellites and never loses its signal. This magnetic memory was imprinted into its brain on the very night it was born. Decades ago, as a tiny, vulnerable hatchling scrambling blindly out of a dark, sandy nest and rushing toward the foam of the breaking waves, it recorded the exact magnetic signature of that specific shoreline. Now, a lifetime later, separated by thousands of miles of open water, that invisible tether still holds. It guides a turtle precisely across oceans where brutal storms obscure the sun and massive currents unpredictably shift. Suddenly, the rhythm of the turtle's underwater flight changes. It angles its streamlined body upward, kicking steadily toward the shimmering surface above. The turtle is a creature caught between two worlds. Though it spends its entire life submerged in the sea, it remains a reptile, bound to the surface of the earth by the absolute biological necessity of oxygen. It breaks the surface, the water shedding rapidly from its smooth, scaled head, and it exhales with a sharp, percussive hiss that sends a fine mist of seawater into the air. In a fraction of a second, it inhales deeply, filling massive, highly adapted lungs with fresh air before slipping silently back beneath the waves, leaving barely a ripple behind. Once submerged, the turtle initiates a physiological magic trick. It does not simply hold its breath in the way a human does. It fundamentally alters its own state of being. As it descends back into the water column, its metabolism begins to plummet. The heart, which might beat quickly during the physical exertion at the surface, slows down to a rhythmic, deliberate crawl. It can drop to just a few solitary beats per minute. Blood vessels throughout its body constrict, actively pulling oxygen-rich blood away from the outer extremities and redirecting it exclusively to the most vital organs, the brain and the heart. The turtle essentially enters a state of suspended animation while remaining in continuous motion. In this chilled, slowed-down state, a resting green sea turtle can remain underwater for astonishing amounts of time. Even while actively swimming against currents, it manages its oxygen supply so perfectly that it can stay submerged for extensive periods, entirely unbothered by the crushing pressure or the suffocating depth. It even manages its own body heat. Unlike most marine reptiles that are entirely at the mercy of the surrounding water's temperature, the green sea turtle's large physical bulk and insulating layers of fat trap the heat generated by its own working muscles. This internal warmth allows it to traverse cold, deep ocean currents that would paralyze other cold-blooded creatures, keeping its vital systems running smoothly in the chill of the abyss. Eventually, the deep, endless blue begins to lighten, shifting from a dark, foreboding navy to a brilliant, glowing turquoise. The open ocean gives way to the coastal shallows, the outer edges of vibrant, sun-drenched coral reef lagoon. The turtle glides effortlessly over the jagged reef crest, entering a world flooded with tropical sunlight and chaotic, swirling life. It lowers its trajectory, sinking slowly toward the sandy bottom where the landscape transforms into a vast, underwater prairie. This is a seagrass meadow, its long green blades swaying gently, hypnotically in the tidal surge. To the untrained eye, it might look like just a patch of underwater weeds. To the green sea turtle, it is an endless, sustaining landscape, and to the broader ocean ecosystem, it is a critical engine of life. The adult green sea turtle is entirely unique among its kin. While other sea turtle species might spend their lives hunting drifting jellyfish, crushing hard-shell crabs, or scavenging for sponges, the adult green turtle is a dedicated, highly specialized herbivore. It settles softly onto the seagrass bed, using its powerful front flippers to stabilize its heavy body against the pull of the gentle current. It lowers its head and begins to feed. The edges of its lower jaw are heavily serrated, acting exactly like a pair of sharp biological shears. It doesn't just bite indiscriminately, and it certainly doesn't rip the grass out by its roots. Instead, it precisely crops the blades, leaving the base of the plant firmly intact in the sediment. This is not just feeding. This is an ancient form of underwater gardening. By constantly cropping the top layers of seagrass, the turtle prevents the blades from growing old, tall, and covered in choking algae or parasitic organisms known as epiphytes. If the grass were left alone, unbothered by grazers, these epiphytes would multiply rapidly, coating the blades and blocking the vital sunlight. The grass would begin to rot. The roots would weaken, and the entire meadow would slowly suffocate and die, turning into a barren wasteland of dead organic matter. But because of the turtle's continuous, meticulous mowing, the seagrass is forced to constantly sprout fresh, healthy, nutrient-rich new shoots. The meadow remains highly productive, a dense, thriving forest of vibrant green. This localized algae farming effect echoes outward to the entire marine food web. Because the turtle keeps the meadow healthy and growing, the deep seagrass roots can continue to anchor the loose sand, preventing devastating coastal erosion when violent storm surges strike the shoreline. Furthermore, the dense, healthy canopy of grass becomes a vital, life-saving nursery. Countless species of commercially and ecologically important fish, tiny, fragile crustaceans, and delicate mollusks use this exact meadow to lay their eggs and hide their young from the sharp-eyed predators patrolling the open water above. Without the grazing turtle, the meadow dies. Without the meadow, the juvenile fish have no shelter, and they are quickly devoured or perish from lack of food. Without the small fish, the larger reef predators, the groupers, the snappers, the barracudas, eventually starve and abandon the reef. The very existence of this vibrant, multi-layered coastal ecosystem rests squarely on the broad, olive-green back of the grazing turtle. It is a true ecosystem engineer, unknowingly shaping and sustaining the world around it with every single bite of grass it takes. But the turtle cannot stay in this idyllic, sunlit garden forever. Deep within its biology, a biological clock strikes. An urge older than the oceans themselves takes absolute hold over the animal's mind, the undeniable urge to reproduce. To do this, the turtle must leave the safety, warmth, and abundance of the coastal feeding grounds. It must embark on a migration that defies human comprehension. It turns away from the shallow coast, pointing its shell toward the boundless blue void once again. The journey ahead may cover thousands upon thousands of miles. It will swim continuously for weeks, perhaps even months. It will push its body through raging surface storms that churn the water into a white froth. It will have to evade the jaws of massive pelagic predators, like tiger sharks and great whites, that track the migratory routes of turtles. It will fight against powerful, shifting ocean currents that threaten to push it hundreds of miles off course. Through it all, it relies entirely on its internal magnetic compass, drawn by an invisible, irresistible force back to the exact geographical coordinates of its birth. When it finally arrives at the destined coastline, it does not immediately approach the shore. It waits just beyond the breakers for the safety and cover of deep darkness. The sea, which has effortlessly supported its massive bulk for decades, suddenly releases it to the crushing, unrelenting pull of gravity. The female turtle drags her heavy, armored body out of the crashing surf and onto the dry, abrasive sand. Every single movement is a colossal, agonizing effort. She must use her flippers, perfectly designed for frictionless flight through a liquid medium, to haul hundreds of pounds of dead weight up the steeply sloping beach. She breathes heavily, laboring under her own weight as she searches for the perfect spot, well past a high tide line where the water cannot reach. Once she finds the right consistency of sand, the digging begins. For hours she works, entering a deep, trance-like state. Using her rear flippers like highly articulated spades, she meticulously scoops out a deep, teardrop-shaped chamber in the cool, moist sand. There in the dark hollow, she deposits a clutch of soft, round, leathery eggs, perhaps 100 or more. This is the next generation of ocean navigators, entirely vulnerable and hidden beneath the earth. She buries them carefully, packing the sand down tightly, and then uses her powerful front flippers to throw loose sand wildly in all directions, intentionally disguising the location of the nest to confuse foxes, crabs, and birds that might seek out the eggs. The effort is totally exhausting. Finally, her ancient task complete, she turns back toward the sound of the crashing waves. Thick, salty tears stream continually from her eyes, not from emotion, but from special glands working to flush the irritating sand and excess sea salt from her face. She drags herself back down the slope. The moment the first wave washes over her shell, the heavy burden of gravity is lifted. She is weightless once more. She flies forward into the dark, welcoming water, leaving her offspring behind to the warmth of the incubating sun and to a vast, unwritten future in the open sea. Back in the calm, protected waters of the reef lagoon, as the sun dips completely below the horizon, the water takes on a bruised, twilight hue of deep purple and black. The brightly colored daytime creatures retreat to their hidden crevices, and the shadowy, nocturnal hunters begin to emerge from the coral caves. A green sea turtle, perhaps resting between long feeding sessions or preparing its body for the grueling migration ahead, finds a deep, cavernous overhang beneath a massive coral head. It swims smoothly into the darkness and wedges its smooth shell tightly beneath the rock roof, finding a secure, sheltered pocket entirely safe from the shifting night currents and the jaws of roaming sharks. It closes its dark eyes. Its heart rate drops down once again to that familiar, rhythmic, crawling pace. The ocean continues to move around it, a constant, endless thrum of life and death, of microscopic battles, of shifting currents and pulling tides. Yet the turtle remains perfectly, absolutely still, a silent, armored monolith of endurance. It is a creature born of the Earth's deep magnetic hum, fueled by the underwater gardens it tirelessly and perfectly tends, and built to fly to the darkest, deepest abyss. In the dark, quiet sanctuary of the sleeping reef, the great navigator rests, waiting only for the dawn and for the endless, ancient journey to begin all over again. The shallow coastal waters of the tropical Pacific present a masterclass in visual deception. In the early hours of the morning, when the sun is just beginning to climb above the horizon, the tide drifts quietly across pale, rippled sand flats. It is a world painted in soft, inviting colors. Scattered fragments of ancient coral skeletons, worn impossibly smooth by the ceaseless grinding of the tides, rest among lush, swaying patches of seagrass. Shafts of sunlight filter down to the surface, breaking into dancing, golden beams that sway in perfect, hypnotic rhythm with the coastal currents. To any observer standing on the shore, or even wading into gentle surf, this environment feels uniquely peaceful, a tranquil nursery bathed in warmth and light. Small, silver-scaled fish hover nervously above the seagrass blades, darting away at the slightest shifting shadow. Juvenile crabs, no larger than a thumbnail, emerge with extreme caution from tiny, perfectly rounded burrows etched deep into the soft sediment. It is a landscape that appears fragile, almost entirely devoid of malice. Yet, suspended within the seemingly innocent and tranquil nursery moves one of the most brutally efficient, highly evolved, and deeply enigmatic predators the ocean has ever engineered. It is an animal whose method of attack unfolds at a velocity that shatters the boundaries of human comprehension, and whose primary weapon is its absolute, terrifying invisibility. Drifting just inches above the sandy floor, nearly impossible to distinguish from the shifting light itself, a boxed jellyfish glides forward. If you were to somehow see it from a distance, it would appear not as a solid creature, but as a ghost, a fleeting, translucent distortion in the water column. Its body is so profoundly transparent that only the faintest, iridescent outlines reveal its physical presence in the world, looking as though the ocean water itself has spontaneously gathered into a delicate, pulsing geometric form. The central bell resembles a flawlessly clear cube with gently rounded, softened edges. From each of the four lower corners of this living cube trails a cluster of long, impossibly thin tentacles that drift lazily behind it, like strands of liquefied glass moving in the current. This transparency is not a mere accident of biology, nor is it simply an aesthetic marvel. It is a highly calculated, ruthlessly refined survival strategy honed over millions of years of evolutionary pressure. In these bright, sun-drenched coastal shallows with boxed jellyfish hunts, the entire ecosystem relies heavily on vision. Prey species constantly scan the bright water for contrasting shapes, dark silhouettes, or the sudden, erratic movements of approaching hunters. By allowing the brilliant tropical sunlight to pass almost entirely unhindered through its gelatinous tissues, the boxed jellyfish completely eliminates the visual contrast that would betray its outline. It casts virtually no shadow. It reflects almost no light. A school of young fish, seeking the protective shelter of the seagrass meadow, might casually swim within a few bare centimeters of the predator, completely unaware that lethal danger is floating quietly right beside them. Despite the profound simplicity suggested by its delicate, gelatinous appearance, the boxed jellyfish is the absolute opposite of a passive drifter. Most jellyfish are the utter mercy of the ocean's whims, carried aimlessly by shifting tides and powerful offshore currents, waiting blindly for food to bump into them. The boxed jellyfish, however, commands its own trajectory. It possesses a remarkable ability to swim with deliberate, predatory control. Lining the smooth interior of its cubic bell is a complex network of highly specialized muscle fibers. As the jellyfish hunts, these muscles contract in a powerful, synchronized, and rhythmic pulse, violently forcing water downward out of the bell cavity in short, highly concentrated bursts. Each pulse acts as a biological jet engine, generating a gentle but firm thrust that propels the animal forward through the water column. While this movement is not particularly fast when compared to the explosive acceleration of a barracuda or a reef shark, it provides a jellyfish with a level of directional control and maneuverability that is virtually unmatched among gelatinous organisms. It allows the creature to actively patrol through the highly complex, obstacle-filled habitats of coastal reefs and dense seagrass beds, turning these tranquil underwater nurseries into its own personal hunting territories. As the jellyfish glides silently above the green meadow, its trailing tentacles fan out, extending backward in graceful, sweeping arcs. Depending on the exact species and the age of the animal, these delicate threads can reach several meters in length, casting a massive, invisible net to the water column. At first glance, They look like nothing more than fragile filaments of silk. But zoom in closer, down to the microscopic level, and a different, horrifying reality emerges. Every single millimeter of these tentacles is armed with a shockingly dense arsenal of highly complex, microscopic weaponry. Embedded by the millions across the surface of the tentacles are specialized, single-celled weapons known as nematocysts. These cells represent what is arguably the most sophisticated, devastatingly fast venom delivery system in the entire natural world. Inside every single nematocyst lies a tightly coiled, microscopically sharp harpoon. This harpoon is packed inside a tiny biological capsule under extreme, almost unimaginable internal pressure, often reaching over 150 atmospheres, roughly the equivalent of the pressure found thousands of feet at the bottom of the ocean. It is a biological spring, wound tight, waiting only for the slightest trigger. The base of this tiny harpoon is connected to a hollow, microscopic tubule, a perfectly designed pipeline through which lethal venom will instantly flow once a mechanism is fired. The box jellyfish continues its slow, pulsing patrol. A small fish, distracted by a drifting speck of edible plankton, swims slightly too close. It moves cautiously, its large eyes darting rapidly as it scans the surrounding water for the dark shapes of predatory birds above or the sleek silhouettes of predatory fish below. But the jellyfish's transparent, glass-like body registers as absolutely nothing to the fish's visual cortex. The fish shifts its tail, altering its course by just a fraction of an inch, and in doing so, it brushes impossibly lightly against one of the drifting, invisible tentacles. That single, microscopic graze is all it takes. On the surface of the tentacle, tiny, hair-like sensory triggers, tuned to detect both the mechanical pressure of a touch and the specific chemical signature of fish skin, are instantly activated. What happens next occurs in a time frame so small it defies human perception. Mechanical and chemical sensors unlock the pressurized capsule. The microscopic harpoons explode outward from the surface of the tentacle. The speed of this violent discharge is truly extraordinary. The harpoon accelerates from a complete standstill to its maximum extension in an interval measured in mere microseconds. It is one of the fastest-moving cellular processes ever recorded in biology, moving with an acceleration that rivals the firing of a bullet from a high-powered rifle. For the fish, there is no time to flinch. There is no time to process the sensation of touch, no time for its brain to send an escape signal to its muscles, and certainly no time to swim away. Hundreds, perhaps thousands, of these microscopic needle-sharp projectiles violently penetrate the fish's scales and skin simultaneously. Each harpoon punches deep into the underlying tissue, acting as a microscopic syringe, injecting a highly concentrated dose of phenomenally potent venom directly through its hollow shaft. The biochemical warfare that ensues is shockingly fast and ruthlessly efficient. The venom immediately floods into the fish's bloodstream and surrounding tissues, aggressively attacking critical physiological systems on a cellular level. Box jellyfish venom is chemically complex, a cocktail of destructive proteins, but is most notoriously feared for its catastrophic ability to interfere with the electrical signaling that controls the beating heart. Specialized, highly toxic compounds within the venom rapidly target and disrupt the delicate membranes of heart muscle cells. They force open microscopic pores in the cell walls, completely altering the natural, carefully balanced movement of sodium, potassium, and calcium ions that regulate muscular contraction. As these ions flood chaotically across the cell membranes, the electrical rhythm of the heart is instantly thrown into absolute chaos. In severe exposures, this devastating cellular disruption causes the heart muscle to seize, violently losing its coordinated rhythm and locking up entirely. It triggers massive, instantaneous cardiovascular collapse. In the small fish now violently entangled within transparent tentacles, the effects unfold in a matter of seconds. The fish's body convulses briefly, a final, chaotic misfiring of its own nervous system as its muscles entirely lose their ability to respond. Its heart stops. Within moments, the prey is completely paralyzed, immobilized in the water, suspended in the lethal grip of the phantom predator. But how does the jellyfish know it has made a kill? It has no brain to process the event, no central command center to formulate a plan of action. Yet it reacts with perfect, coordinated purpose. The jellyfish senses a struggling, capture prey through a surprisingly capable, completely decentralized nervous system. Rather than concentrating its neurons into a single, vulnerable brain, the box jellyfish features a complex, ring-shaped nerve network that circles the very base of its bell, with extending branches that run deep down the length of every tentacle. This continuous ring of nerves functions as a highly efficient coordinating hub. It acts as a biological circuit board, seamlessly linking sensory inputs from the tentacles to the powerful swimming muscles lining the bell. When the nematocysts fire and the tentacles register the weight and chemical signature of captured prey, electrical signals flash up the nerve ring. Instantly, the jellyfish's behavior changes. The bell begins to pulse with a modified, more active rhythm, fighting the resistance of the water, as a specific tentacle holding the prey begins to retract. Slowly, methodically, it draws the immobilized fish upward through the water column, pulling it closer and closer to the gelatinous body above. As the paralyzed fish reaches the base of the central bell, the jellyfish performs a feat of alien anatomy. It folds portions of its lower body inward, manipulating its own tissues to guide the dead prey precisely toward its mouth, which is located on a short, tube-like structure hanging directly down from the center of the underside of the bell. Highly specialized, digestive tissues begin to slowly envelop the fish. Powerful enzymes are secreted, initiating the slow, dissolving process of breaking down complex proteins, muscle fibers, and internal organs into a nutrient-rich biological soup. These life-sustaining nutrients are then absorbed directly through the walls of the jellyfish's internal stomach cavity, rapidly providing the massive amounts of metabolic energy required to fuel its continuous swimming and, crucially, the constant regeneration of its millions of microscopic, venomous harpoons. The sensory capabilities of this brainless hunter do not end with simple touch or chemical recognition. In one of the most astonishing evolutionary developments in the invertebrate world, the box jellyfish possesses a highly sophisticated set of visual organs. Located at specific intervals around the lower margin of the transparent bell are specialized sensory structures called rhopalia. Each individual rhopalium is a tiny, self-contained sensory hub, and contained within them are actual eyes. Unlike the simple, primitive light-sensing eye spots found on most other jellyfish species, which can only tell the difference between light and shadow, the box jellyfish possesses incredibly complex visual equipment. Each rhopalium contains multiple distinct types of eyes, complete with actual corneas, specialized spherical lenses, and complex retinas capable of forming distinct, focused images of the world around them. Even without a central brain to process this complex visual data, the decentralized nerve ring interprets the signals from these eyes in real time. It allows the jellyfish to actively scan its environment, to detect solid physical obstacles like rocks or coral heads, to navigate purposefully toward the darker, safer environments of mangrove roots or seagrass meadows, and potentially even to actively track the physical movements of prey swimming within the water column. It is a creature that can see you, track you, and hunt you, all without possessing a single thought. In these shallow tropical waters, the box jellyfish occupies a highly unusual and terrifying ecological niche. Most gelatinozoa are passive participants in the ocean's food web, drifting aimlessly and feeding almost exclusively on microscopic organisms or tiny plankton that happen to fall into their path. Box jellyfish, by stark contrast, are highly active, apex micropredators. Their ability to swim with direction, to see their environment, and to deliver instantaneous, lethal chemical strikes allows them to actively patrol the very coastal habitats where juvenile fish gather for safety. They turn these tranquil, sunlit nursery grounds into highly effective, invisible hunting territories. Yet, despite their incredibly fearsome reputation, a reputation deeply respected by human coastal communities who understand that a severe sting from certain species can produce agonizing pain and systemic cardiovascular failure in a human within minutes, the box jellyfish remains an integral, balanced component of marine ecosystem. Its relentless predation helps carefully regulate the exploding populations of small fish and tiny crustaceans that inhabit the shallow tropical waters, preventing any one species from over-consuming the resources of the reef. And, in the grand, unending cycle of ocean life, even this venomous phantom is not invincible. The box jellyfish itself falls prey to specialized, highly adapted hunters. Massive sea turtles, specifically the leatherback and the green sea turtle, possess thick, armored skin and specialized, heavily lined throats that render them virtually immune to the jellyfish's catastrophic sting. They actively hunt the transparent cubes, treating one of the ocean's most deadly predators as little more than a floating, gelatinous snack. These interactions illustrate the beautiful, ruthless, and delicate balance within marine food webs. Even the most highly venomous, perfectly camouflaged organisms remain vulnerable within the broader, unyielding ecological network. As the morning progresses toward midday, the sun climbs higher into the brilliant sky, and the coastal lagoon grows brighter, warmer, and ever more active. Large schools of juvenile fish gather in massive, shimmering clusters above the green seagrass meadow, while larger, predatory trevally and jacks begin to aggressively cruise the outer edges of the reef in search of an easy meal. Amidst this chaotic explosion of color, sound, and motion, the box jellyfish continues its slow, completely silent patrol. It pulses steadily, rhythmically through the bright water, its lethal tentacles drifting imperceptibly behind it. Within this transparent hunter lies a profoundly sophisticated biological system built entirely around speed, advanced chemistry, and total visual stealth. Its millions of microscopic harpoons remain tightly coiled, heavily pressurized, and perfectly primed along the length of every tentacle, waiting with infinite patience for the next accidental brush from an unsuspecting animal. The ring-shaped nervous network coordinates the jellyfish's movements with quiet mechanical efficiency, guiding its pulses through the subtle, shifting changes in tropical light and coastal water currents. Beneath the shimmering, mirror-like surface of the lagoon, the predator drifts onward, utterly invisible to the frantic creatures swarming around it. In this unforgiving world of shifting tides, hidden dangers, and constant, unending competition, the box jellyfish stands as a flawless demonstration that true complexity in nature does not always require rigid bones, a massive brain, or displays of visible, muscular strength. Sometimes the absolute most effective, terrifying predator in the ecosystem is the one that completely dissolves into the environment itself. It carries its weapons not in the form of crushing jaws or tearing claws, but in the shape of microscopic darts that strike exponentially faster than sight. Through hundreds of millions of years of isolated evolution, this delicate, floating cube of living tissue has perfected one of the fastest, most deadly venom delivery systems on the planet, transforming the gentle, beautiful motion of drifting tentacles into a lethal, unavoidable encounter that begins and ends in less time than the blink of an eye. Plunge into the frigid, nutrient-choked currents that continuously hammer the southern coastlines of the Australian continent. Here, the ocean does not resemble the bright, sun-baked coral gardens of the tropics. Instead, it offers a sprawling, shadowy submarine wilderness, a vast underwater woodland that rivals the density and complexity of any terrestrial rainforest. This is the realm of the giant kelp. Massive, monolithic stalks of golden-brown algae rise from the rocky, storm-swept seabed, reaching desperately upward toward the faint, filtered sunlight far above. These towering aquatic plants form a labyrinthine canopy, a dense ceiling that blocks the harsh surface light and casts the world below into a state of perpetual, shifting twilight. The water here is heavy, cold, and relentlessly thick with suspended plankton and drifting organic matter. The oceanic currents do not race through this forest. They weave and push, forcing the millions of long, leathery kelp fronds to sway in a synchronized, hypnotic rhythm. It is a mesmerizing, almost dizzying environment to navigate for the predators that patrol the dark outer edges of these underwater woods, the sleek, fast-moving reef fishes and the sharp-eyed sharks. Hunting is an exercise in intense visual focus. They must constantly scan this swaying, chaotic landscape for the telltale silhouette of fish, for the panic dart of prey item breaking the rhythmic, natural motion of the algae. But deep within the heart of this shifting, golden-green forest, suspended perfectly within the rhythmic sway of the ocean surge, exists an absolute masterpiece of evolutionary deception. It glides through the shadows with an eerie, ghost-like grace. It does not look like an animal. It does not move like an animal. To the eyes of any passing predator, it is nothing more than a broken, drifting piece of seaweed, torn from its holdfast by a distant storm and left to wander aimlessly in the tide. Yet, this drifting fragment is intensely alive. It is the Leafy sea dragon, a creature that has completely surrendered its physical identity to the environment it calls home. To gaze upon a leafy sea dragon is to witness the absolute extreme of morphological camouflage. Unlike the mimic octopus or the cuttlefish, which rely on highly complex, rapid neurological commands to instantly change the color and pattern of their skin, the sea dragon's disguise is etched permanently into its very bones and flesh. Through millions of years of relentless selective pressure, where the slightest visual mistake meant instant death in the jaws of a passing predator, the sea dragon's entire body plan has been radically sculpted to become a flawless, living imitation of the kelp, extending outward from its incredibly slender, almost fragile-looking body are dozens of elaborate, highly irregular, leaf-like appendages. These are not fins designed to push water. They possess absolutely no aerodynamic or hydrodynamic function for swimming. They are purely, exclusively ornamental, fleshy extensions of skin designed with one single, spectacular purpose: visual misdirection. These structures branch and fork outward in highly delicate, chaotic shapes, perfectly mirroring the torn, frayed, and ragged edges of dying kelp blades that naturally drift through the forest. The coloration of the sea dragon is a masterclass in muted, environmental matching. It is completely devoid of the brilliant, flashing warning colors so commonly found on tropical reefs. Instead, its skin is painted in the exact, somber palette of the Southern Ocean. Subdued shades of olive green, sickly pale yellow, and deep, muddy brown blend across its highly irregular body in patterns that flawlessly echo the decaying algae around it. But the illusion goes even deeper than shape and color. Evolution has even altered the microscopic texture of the sea dragon's skin. The surface of its body is not covered in smooth, highly reflective scales like a typical fish, which would immediately betray its presence with a silver flash of sunlight. Instead, its skin is covered in thousands of tiny, irregular ridges, microscopic bumps, and rough, uneven surfaces. This specific texture is designed to scatter and absorb incoming light in the exact same manner as the natural, slightly slimy sheen of a kelp leaf. When viewed from even a few feet away, the physical boundaries of the animal completely dissolve. The sea dragon ceases to be a fish. It becomes a forest. Yet, underneath this elaborate, plant-like costume, the leafy sea dragon remains a highly specialized, highly effective predator in its own right. It just operates on a vastly different scale and speed than the sharks that circle it home. Extending from the front of its heavily camouflaged head is a long, rigid, tubular snout. At the very end of this tube is a tiny, almost imperceptible mouth. The sea dragon does not possess powerful, crushing jaws or rows of serrated teeth. It does not actively chase down its meals. Instead, it relies on the lethal element of surprise, coupled with the raw physics of fluid dynamics. As it drifts invisibly through the water column, its large, independently moving eyes continuously scan the surrounding water for microscopic prey. Swarms of tiny shrimp-like crustaceans called mysids, along with various forms of drifting zooplankton, form the bulk of its diet. These tiny creatures are highly sensitive to changes in water pressure and will violently dart away from the approaching pressure wave of a standard swimming fish. But the sea dragon generates almost no pressure wave. It simply drifts into their presence, a harmless-looking leaf floating by. When a cluster of tiny crustaceans drifts within a fraction of an inch of its snout, the sea dragon strikes. In a movement too fast for the human eye to track, specialized bones and muscles in the sea dragon's throat violently expand. This rapid internal expansion creates an instantaneous, catastrophic drop in pressure within the tubular snout. A miniature, localized vacuum is formed. The water immediately surrounding the mouth, along with the completely unsuspecting prey, is violently sucked inward with sharp, clicking sound. The prey is swallowed whole, entirely intact, before it even registers a change in the current. The strike is so localized, and the sea dragon's body remains so perfectly still during the process, that the surrounding swarms of crustaceans often don't even realize they are being systematically hunted. The sea dragon consumes thousands of these tiny creatures every single day, completely invisible to the microscopic life it devours, and completely invisible to the massive predators that could devour it. But the true genius of the leafy sea dragon lies in the way it moves. Camouflage is absolutely useless if an animal's behavior betrays its disguise. If a creature looks exactly like a piece of drifting seaweed, but suddenly sprints forward with explosive, side-to-side tail sweeps of a fleeing fish, The illusion is instantly broken and the predator strikes. The sea dragon has therefore abandoned traditional swimming entirely. It does not use its tail for propulsion. In fact, its tail is relatively stiff and primarily used simply for anchoring itself to a solid stalk of kelp during exceptionally violent ocean storms. To move through the water, the sea dragon relies on a set of nearly invisible, highly translucent fins that are almost impossible to detect unless you are looking for them. Located along the ridge of its spine, tucked behind elaborate fleshy leaves, is a small, completely clear dorsal fin. Near the sides of its head, nestled behind its gills, are two equally transparent pectoral fins. These fins beat at an incredibly high frequency, oscillating back and forth dozens of times per second. Because they are clear, they create no visual disruption. Because they are small, they create virtually no acoustic disturbance in the water. This rapid, localized fluttering provides a gentle, remarkably steady forward propulsion, while the pectoral fins offer highly precise, micro-adjustments for steering and balance. As the sea dragon glides through the kelp forest, its movement is eerily smooth. It does not jerk or dart. It moves with the exact lazy, unstructured drifting motion of unattached algae. As the powerful ocean surge pushes through the kelp forest, forcing the giant plants to bend and sway, the sea dragon allows itself to be pushed exactly in tandem with the surge. It does not fight the current. It surrenders to it, riding the ebb and flow, turning its entire method of locomotion into an extension of its camouflage. To a predator whose brain is hardwired to recognize the distinct, muscular movements of living prey, the sea dragon offers absolutely no recognizable biological cues. It simply exists as a part of the background, a ghost in the weeds. This total commitment to stealth and camouflage extends even into the most vulnerable, dangerous phase of any animal's life: reproduction. In the brutal environment of the ocean, leaving eggs defenseless on the seafloor is practically an invitation for them to be devoured by opportunistic scavengers. Many fish species produce millions of eggs and scatter them blindly into the current, hoping that sheer numbers will guarantee the survival of a few. The sea dragon, however, closely related to the seahorses and pipefish, employs a radically different, highly invested strategy. It completely subverts traditional gender roles to ensure the safety of the next generation. In the world of the sea dragon, it is not the female who bears a heavy, dangerous burden of pregnancy. It is the male. As the mating season arrives, the male and female engage in a slow, elegant, mirroring dance, rising and falling together to the water column, completely synchronized. During this intricate courtship, the female prepares her eggs, but she does not release them into water. Instead, she carefully, directly transfers a massive cluster of brilliant, bright pink eggs directly onto the male's body. Specifically, she deposits them onto a highly specialized, modified patch of tissue located firmly beneath his tail. Unlike male seahorses, which possess a closed, internal pouch to hide their young, the male Leafy sea dragon has no such enclosure. His brood patch is completely exposed to the open ocean. However, this patch is incredibly complex. It is a spongy, highly vascularized matrix of tissue, incredibly rich in blood vessels. As the female presses the eggs onto his tail, the spongy tissue immediately swells, forming tiny, individual indentations, biological cups, that securely anchor each and every egg in place. The male sea dragon is now a living, swimming nursery. For several agonizingly long weeks, he will carry dozens of developing embryos exposed on his tail. The vascular network of the spongy tissue connects directly to the eggs, acting much like a mammalian placenta, constantly pumping vital, life-sustaining oxygen and necessary nutrients directly from the father's bloodstream to the thin membranes of the eggs. It is an immense physical toll on the male. He becomes slower, heavier, and requiring even more energy to sustain both himself and his unborn young. Yet, this bizarre reproductive strategy is an evolutionary masterstroke. By carrying the bright pink eggs directly attached to his heavily camouflaged body, the male ensures that the developing embryos are constantly shrouded by the exact same flawless disguise that protects him. An unprotected cluster of bright pink eggs resting on the dark ocean floor will be discovered and eaten within hours. But attached to the tail of a father who looks exactly like a drifting piece of seaweed, they become completely invisible. The male continues his slow, drifting patrol through the kelp, maintaining his meticulous illusion, guarding his offspring by simply refusing to be seen. As the weeks pass, the bright pink color of the egg slowly begins to fade, shifting to a duller, translucent brown. If you would look closely enough, peering through the thin, leathery shells, you would see a miracle of biology unfolding. Deep within the eggs, tiny, perfectly formed miniature dragons are beginning to stir. They possess the exact same elaborate, leaf-like appendages, the exact same long, tubular snouts, and the exact same large, observant eyes as their parents. They are born fully equipped for grand illusion. When the moment of hatching finally arrives, there is no dramatic struggle. The tiny sea dragons simply burst from their casings and immediately begin to drift into surrounding water. They are entirely independent from the very first second of their lives. Unlike the microscopic, planktonic larvae of so many other marine species, they're swept hundreds of miles out into barren, open ocean. The juvenile sea dragons are designed to stay local. They instinctively remain deep within the tangled, protective sanctuary of the kelp forest. This environment is not just a backdrop. It is their absolute salvation. The kelp forest breaks the force of the massive ocean currents that could easily sweep their fragile bodies out to sea. It provides an endless, winding labyrinth of hiding places, completely shielding them from the sight of passing predators. And it is teeming with the microscopic crustacean life they need to fuel their incredibly rapid growth. They immediately begin a delicate, swaying dance of their ancestors, blending instantly into the golden brown shadows. As the afternoon light shifts across the dense canopy of the kelp forest, long, undulating shadows ripple continuously across the rocky seafloor. The adult male sea dragon, his heavy reproductive burden finally lifted, drifts quietly back into the dense undergrowth. His body remains completely indistinguishable from the swaying vegetation that entirely engulfs him. Every subtle, fluttering movement of his transparent fins carries him forward with such minimal disturbance that the water itself barely registers as passing. In an oceanic world where survival is so often dictated by raw, explosive speed, aggressive armor, or terrifying displays of brute force, the Leafy sea dragon stands as a profound testament to a completely different evolutionary philosophy. Its survival does not depend on outrunning its enemies or overpowering its prey. It depends on absolute patience, unparalleled subtlety, and extraordinary, almost magical ability to become an inseparable part of the landscape itself. Through millions of years of ruthless, unbroken natural selection, its body has been forged into a living, breathing extension of the ancient kelp forest. It is a creature whose very identity has merged with the plants that surround it. Among the slowly swaying fronds of algae, caught in the eternal, rhythmic pull of the southern ocean currents, the Leafy sea dragon continues its silent, secretive existence. Its disguise remains absolutely perfect. Its movements remain painfully slow, meticulously deliberate, and flawlessly in tune with the pulse of the sea. Its presence is revealed only to those who look closely enough, long enough, and deeply enough to see the living animal hiding flawlessly within the forest of leaves. In this delicate razor-thin balance between illusion and brutal reality, the Leafy sea dragon stands as one of the ocean's most breathtaking, uncompromising examples of evolutionary artistry, a phantom of the kelp, hiding endlessly in plain sight. The tropical sun breaches the horizon, sending heavy, angled beams of pure light slicing through the crystal-clear water of the shallow reef. From a distance, this brightly illuminated underwater city appears entirely at peace. Gentle currents wash over towering spires of branching coral. Schools of vivid, neon-colored fish weave through the limestone labyrinth, and the ocean floor seems locked in a state of quiet, eternal tranquility. But this serene facade is an illusion. To truly understand the coral reef, you must strip away the romance and look closer at the brutal reality of the ecosystem. This is not a peaceful garden. It is a claustrophobic, fiercely contested battlefield. Every single square centimeter of hard surface on the reef is the subject of merciless, unending war for real estate. Coral polyps fight desperately for space to grow and reach the sunlight. Sponges expand to smother their neighbors. And above all, fast-growing, aggressive algae constantly threaten to overrun the entire landscape, plunging the delicate corals into darkness and suffocating the life out of limestone foundations. In this agonizingly slow but deadly war of inches, the survival of the entire underwater city depends heavily on the relentless, grinding work a creature that, to the casual observer, appears to be nothing more than a lifeless, immobile rock, nestled deeply into a jagged crevice between two massive boulders of ancient coral, sits the sea urchin. It is a sphere of absolute, unapologetic defiance. It lacks the streamlined, muscular grace of a hunting shark. It does not possess the hypnotic, color-shifting camouflage of a cephalopod, nor the explosive, terrifying speed of a striking barracuda. It has no face, no recognizable brain, and no heart in the traditional sense. It appears simply as a dark, bristling orb, an impenetrable fortress of sharp, radiating needles resting silently on the seafloor. But do not mistake its stillness for lifelessness. The sea urchin's defensive armor is an absolute marvel of biological engineering. The creature is completely encased in hundreds of slender, incredibly sharp spines that point outward in every conceivable direction, creating a dense, three-dimensional phalanx of spears. These spines are not rigidly fixed to the body like the thorns on a rose bush. Each individual spine is mounted securely to the underlying shell by a highly complex biological ball and socket joint. This intricate muscular articulation grants the sea urchin an astonishing degree of flexibility. When a shadow passes overhead, or when the subtle pressure waves of an approaching predator disturb the surrounding water, the urchin reacts. Muscles at the base of the spines instantly contract, allowing the animal to pivot and aim its defensive weapons directly toward a perceived threat. For the vast majority of predators roaming the reef, the message is unmistakably clear. Attempting to bite, swallow, or even touch the sea urchin requires navigating a mobile, highly reactive barrier of spikes fully capable of piercing lips, eyes, and the soft tissues of the mouth. The pain and risk of severe, festering injury are so high that most fish instinctively give the creature a wide, respectful berth. Yet, the true genius of this spiny fortress lies in its phenomenal capacity for cellular renewal. The urchin's armor is not a disposable shield. It is a dynamic, living tissue. In the chaotic environment of the reef, damage is inevitable. Violent storm surges can smash heavy debris against the seafloor. Shifting sands can grind against the shell, and desperate, hungry predators will occasionally risk a glancing bite that snaps a spine in half. For many animals, a broken bone or shattered shell is a permanent, potentially fatal vulnerability. For the sea urchin, it is merely a temporary inconvenience. If a spine is fractured or sheared off entirely, the animal does not bleed or succumb to wound. Instead, a highly specialized network of cells deep within the urchin's body springs into immediate action. The biological machinery goes to work at the base of the damaged structure, aggressively synthesizing fresh minerals harvested directly from the surrounding seawater. Slowly, methodically, a new spine begins to extrude from the stump, growing outward millimeter by millimeter, gradually restoring the weapon to its original length, sharpness, and strength. This breathtaking regenerative capability extends far beyond the external spines. Beneath that bristling forest of needles lies the core of the animal's defense, a rigid, hollow shell known to marine biologists as a test. This test is constructed from a perfectly arranged, interlocking geometric mosaic of calcium carbonate plates, seamlessly fused together to protect the delicate internal organs. If a rock falls and cracks the test, or if the immense pressure of a predator's jaws manages to fracture the surface, the sea urchin can actually deposit fresh layers of raw mineral directly into the fissures, knitting the shattered limestone back together from the inside out. It is a self-repairing, living castle, capable of weathering the physical abuse of the ocean for years on end. But the sea urchin is far more than just a defensive bunker waiting out the storm. It is an active, vital participant in the ecology of the reef, and it moves with a slow, mechanical purpose that is entirely invisible to the naked eye. To move across the jagged, uneven terrain of the limestone rock, the urchin utilizes a bizarre and highly effective hydraulic system. Hidden between the dense forest of sharp spines are hundreds of long, incredibly thin, translucent tubes known as tube feet. These delicate appendages are powered entirely by water pressure. By meticulously pumping seawater in and out of microscopic internal reservoirs, the urchin can extend, bend, and contract these tube feet with surprising strength. The tips of the feet are equipped with tiny biological suction cups. As the urchin decides to move, it reaches out with dozens of these feet simultaneously, adhering the suction cups firmly to the rock, and then contracting the hydraulic tubes to slowly, steadily pull its heavy, armored body forward. It is a painfully slow procession, a glacial crawl across the battlefield of the reef. These 2 feet serve a dual purpose. They are not merely the engine of locomotion. They are the creature's primary connection to the sensory world. Lacking eyes, ears, and a nose, the sea urchin uses these highly sensitive, reaching tentacles to literally taste and feel the water around it. The 2 feet detect the faintest chemical trails of food drifting on the current, and they sense the microscopic vibrations of the ocean, painting a complex chemical tactile map of the environment within the urchin's decentralized nervous system. And what is the urchin searching for as it pulls itself across the rock? It is searching for the enemy of the coral, algae. This brings us to the underside of the creature, hidden in the shadows against the rock. Here lies one of the most terrifyingly effective, mechanistically complex feeding apparatuses in the entire animal kingdom. It is a structure so structurally bizarre and perfectly engineered that early scientists named it Aristotle's lantern. Aristotle's lantern is not a simple jaw. It is a massive, circular array of interlocking, calcified plates and highly leveraged muscles that functions exactly like a heavy-duty industrial drill. Arranged in a perfect, converging circle at the center of this apparatus are 5 incredibly sharp, chisel-like teeth. As the sea urchin creeps over a patch of algae-covered rock, the heavy muscles of the lantern rhythmically contract and relax. The 5 teeth extend outward, bite down hard against the solid stone, scrape violently together, and retract back into the mouth. Over and over again, in a relentless, rhythmic cycle, the lantern grinds against the reef. Each passing scrape mercilessly strips away the thick, suffocating layers of algae, along with microscopic layers of solid limestone rock itself. The sheer mechanical force generated by this biological machine is staggering. To scrape solid rock day after day, week after week, would completely shatter the teeth of almost any vertebrate animal. But the sea urchin's teeth are woven from a highly specialized matrix of calcite crystals. These crystals are arranged in complex, microscopic patterns specifically designed to distribute the immense stress of grinding rock evenly throughout the entire tooth, rendering them exceptionally resistant to cracking, wearing, or fracturing. Material scientists have studied these teeth closely, marveling at a biological structure that possesses a mechanical durability and wear resistance of advanced, human-engineered alloys. Even more incredibly, these teeth are entirely self-sharpening and self-renewing. As the very tips of the calcite chisels inevitably wear down from the constant, brutal abrasion against the reef, new tooth material is continuously, endlessly formed at the base of the lantern inside the animal's body. The teeth operate on a permanent conveyor belt of growth, pushing fresh, razor-sharp mineral outward to replace exactly what was lost to the rock. The machinery of Aristotle's lantern never dulls. It never loses its edge. This relentless, grinding hunger is the very salvation of the coral reef ecosystem. Remember the slow-motion war for space. In the warm, nutrient-rich waters of the tropics, algae grows significantly faster than coral. Left completely unchecked, a sudden bloom of fleshy algae would rapidly blanket the entire reef, blocking out the vital sunlight that the corals desperately need to photosynthesize and survive. The coral polyps would choke, die, and the brilliant, colorful underwater city would quickly degrade into a rotting, desolate wasteland. The sea urchin is the ultimate, uncompromising gardener of the reef. By ruthlessly scraping the rock bare, the urchin removes the aggressive algae and, crucially, exposes pristine, perfectly clean patches of white limestone. It is on these freshly scrubbed, completely bare surfaces that new microscopic coral larvae, drifting helplessly in the ocean currents, can finally find a place to attach, settle, and begin growing new colonies. The sea urchin's destructive, grinding hunger is the exact mechanism that fuels the reef's endless cycle of rebirth and expansion. It is a perfect violent harmony. The urchin destroys the stone to save the coral. Of course, even a fortress is not invincible. The evolutionary arms race in the ocean is a never-ending escalation of tactics. While most predators look at the sea urchin and swim away in defeat, a select few have developed highly specialized strategies to bypass the bristling wall of spears. Enter the triggerfish. This large, powerfully built reef predator possesses heavily armored scales and a mouth full of thick, crushing teeth specifically designed for breaking shells. But it does not simply bite the urchin head-on. That would be suicide. Instead, the triggerfish understands the urchin's single, fatal design flaw. The heavy armor and the sharpest spines are concentrated on the top and sides of the animal. The underside, where the tube feet and Aristotle's lantern meet the rock, is significantly flatter and less protected. When a triggerfish spots a sea urchin, it swims aggressively down to the seafloor. It positions its mouth just inches from the sand and violently forcefully blows a targeted, high-pressure jet of water directly under the urchin's body. The sudden, intense hydraulic lift breaks the suction of the tube feet. The urchin loses its grip on the stone and tumbles helplessly backward, flipping over to expose its vulnerable, lightly armored belly. Before the urchin can right itself, the triggerfish lunges, its heavy teeth easily punching to the weaker underside of the test, bypassing the terrifying spines entirely to feast on the nutrient-rich organs within. It is a brutal, sudden end for the armored gardener, but such is the reality of the reef. Even the most heavily defended creatures are locked into grand, unending cycle of predation and energy transfer. Yet, despite the ever-present threats from specialized hunters, despite the raging storms that occasionally tear through the shallows, the sea urchins persist. They have survived in the oceans for hundreds of millions of years, outliving the dinosaurs, quietly scraping away at the rocks beneath the waves. As the afternoon sun shifts, casting long, deep blue shadows across the towering limestone structures of the reef, the urchin remains in place. It does not possess a complex, emotional brain. It does not communicate with its peers through intricate vocalizations. It will never migrate thousands of miles across open ocean basins. It leads an existence of localized mechanical repetition. It extends its hydraulic feet, pulls its heavy armored shell forward a fraction of an inch, and brings the crushing, unyielding weight of Aristotle's lantern down against the stone. Scrape, grind, move. In the grand hierarchy of the ocean's apex predators, the sea urchin is rarely the star of the show. But without this silent, bristling sphere of spines, the magnificent coral cities of the world would simply cease to exist. It is the ultimate foundation of the ecosystem, an organism whose quiet, relentless persistence quite literally shapes the very architecture of the underwater world. It is a living fortress, the tireless gardener, holding the darkness of the algae at bay, one microscopic bite of rock at a time. Plunge into the rolling, steel-gray surface of the North Atlantic, far from the sun-drenched, tranquil coral gardens of the tropics. Here, the ocean is a brutal, unforgiving engine of cold. Freezing currents slide like liquid ice across jagged rocky seabeds, and massive, towering forests of dark kelp sway violently in a relentless, heavy rhythm of the coastal tides. The landscape below resembles a submerged, desolate mountain range, a chaotic topography of massive granite boulders, deep, shadowy crevices, and steep, algae-covered rock walls plummeting into the black abyss. It is a harsh, uncompromising environment where warmth is a luxury and survival is an hourly test of endurance. Yet, moving slowly through the darkest shadows of these stone crevices, navigating the freezing depths with absolute mechanical confidence, is an animal that carries a biological secret so profound it borders on the realm of science fiction. It is a creature whose very existence quietly, stubbornly challenges one of the most fundamental, universal laws of biology. For nearly every living organism on Earth, from the smallest insect to the largest blue whale, time is the ultimate, undefeated predator. Life is defined by a slow, inevitable trajectory of decline. Cells wear down, muscles weaken, reproductive systems fail, and the body eventually succumbs to the accumulated damage of years. This is the aging process. It is a universal certainty. But deep in the freezing Atlantic, the lobster follows an entirely different trajectory. It operates under a biological phenomenon that scientists describe with a phrase that sounds almost mythological: negligible senescence. In simple terms, negligible senescence means that this heavily armored creature does not biologically age. It does not experience the physical deterioration, the loss of strength, or the decline in metabolic function that we associate with growing old. If it is not killed by a predator, a disease, or a human trap, the lobster does not simply wither away and die of old age. It possesses a terrifying, beautiful potential for extreme, almost limitless longevity. Watch as it emerges cautiously from beneath a massive rock ledge, provoked by the shifting tide. Its heavily armored body glows faintly in the dim light, a model canvas of deep reds, muddy browns, and dark greens, disguised beneath a thick, natural coating of algae and ocean sediment that has accumulated across the surface of its shell over years of slow, deliberate living. Too impossibly long, whip-like antennae extend forward from its head, sweeping to the freezing water with slow, methodical, sweeping motions. These antennae are not simply feelers used to blindly tap against rocks. They are incredibly powerful, highly sensitive chemical detectors. The deep ocean can be pitch black, choked with suspended sediment and suffocating darkness. Vision here is often useless. Instead, the lobster perceives its vast, three-dimensional world through an invisible, swirling language of dissolved molecules. The antennae constantly taste the water, detecting the faintest, microscopic chemical traces of a crushed clam miles away, the subtle pheromones of potential mate, or the terrifying, distinct scent of a predatory cod closing in. Through this chemical radar, the lobster reads the ocean currents like a map, navigating the total darkness with absolute, unerring precision. As it steps out of its cave, planting its articulated, clawed legs onto the stone, its true weaponry is revealed. The lobster's front claws represent a fascinating, brutal example of anatomical specialization. They are heavily asymmetrical, each evolved for a highly specific, highly destructive purpose. One claw is significantly larger, a massive, bulbous weapon heavily reinforced with thick calcium carbonate. This is the crusher claw. Powered by incredibly dense, slope-witch muscle fibers, the crusher can generate hundreds of pounds of raw, mechanical pressure per square inch, easily enough to shatter the thick, calcified shells of clams, mussels, and large sea snails with a sickening crunch. The opposite claw is entirely different. It is slender, sleek, and lined with dozens of razor-sharp, serrated teeth. This is a cutter claw, packed with fast twitch muscles designed for explosive speed rather than raw power. The lobster uses his blade to instantly slice through the soft, fleeing flesh of small fish, worms, or shredded carrion, holding the prey perfectly still while the crusher does the heavy work. Armed with this devastating dual arsenal, the lobster operates as both a terrifying ambush predator and the ultimate, opportunistic scavenger of the deep, recycling organic material and maintaining the harsh balance of the coastal ecosystem. But how does a creature so heavy, so heavily armored, manage to defy the absolute laws of aging? To understand the lobster's immortality, you must look deep inside its body, past the heavy shell, down to the microscopic architecture of its DNA. In humans and most other animals, every time a cell divides to repair a wound or replace dead tissue, it must copy its genetic code. At the very ends of our chromosomes are protective caps called telomeres, much like the plastic tips at the ends of shoelaces that keep them from unraveling. With every single cellular division, these telomeres get snipped slightly shorter. Eventually, after decades of living, the telomeres become too short, the cells can no longer divide safely, and they simply shut down. This microscopic unraveling is the very definition of aging. It is why our skin wrinkles, our bones weaken, and our organs fail. The lobster, however, possesses a genetic cheat code. Its cells produce massive, continuous quantities of a highly specialized enzyme known as telomerase. Telomerase is a molecular repair system. Every single time a lobster cell divides, the telomerase enzyme rushes in and meticulously rebuilds the tips of the chromosomes, restoring the telomeres to their original length. The biological clock is instantly, permanently reset. Because the chromosomes never fray, the cells never lose their ability to replicate perfectly. This means a 50-year-old lobster has the exact same cellular vitality, the exact same muscle mass, and the exact same reproductive fertility as a 5-year-old lobster. In fact, because they never stop growing, older lobsters are exponentially stronger, more heavily armored, and capable of producing vastly more offspring than their younger counterparts. They do not weaken. They simply level up, growing ever more massive, ever more dominant, endlessly walking the ocean floor as decades turn into centuries. Yet, this incredible, endless capacity for growth comes with a terrifying, often fatal catch. The lobster's cells may be immortal, but the heavy, rigid armor that protects its body from the brutal ocean is entirely dead. The exoskeleton is made of chitin and calcium. It does not contain living cells, and therefore it cannot stretch and it cannot grow. Imagine being trapped inside a perfectly tailored suit of steel armor, while your body underneath continues to slowly, inevitably expand. The pressure builds. The space becomes claustrophobic, agonizingly tight. To survive its own relentless biological growth, the lobster is forced to undergo one of the most excruciating, perilous, and physically exhausting processes in the entire animal kingdom. The molt. When internal pressure becomes absolute, the lobster's body releases a surge of hormones, signaling that the current shell must be abandoned. The creature retreats into the deepest, darkest, narrowest crevice it can find, completely sealing itself off from the outside world. It stops eating. It stops moving. Deep beneath the heavy, old armor, its skin begins to rapidly secrete enzymes that slowly dissolve the inner layers of the shell, separating the living tissue from the dead calcium. A new, microscopic, incredibly soft and folded exoskeleton begins to form tightly against the lobster's raw flesh. Then, the true ordeal begins. The lobster forcibly absorbs massive quantities of seawater, intentionally swelling its body to create internal pressure until, with a sharp, violent snap, the heavy carapace splits straight down the back. What follows is an agonizing act of full-body extraction. The lobster must slowly, violently pull its entire, swollen body backward out of the shattered shell. Every single limb, every joint, every antenna, and even its delicate eye stalks must be forcefully squeezed and dragged out through incredibly narrow openings. The effort requires a staggering amount of muscular exertion. If the lobster panics, or if a claw gets snagged within the old armor, it must violently sever its own limb to escape, or risk dying trapped halfway between its old life and its new one. When it finally breaks free, collapsing on the seafloor next to the perfect, empty ghost of its former self, the lobster is entirely unrecognizable. It is completely soft, resembling a massive, gelatinous piece of raw meat. It has no armor. Its massive crusher claw is now as soft as a wet sponge, completely incapable of defending the animal. For the next several days, the supposedly immortal king of the reef is reduced to the most vulnerable creature in the ocean. If a hungry cod, an octopus, or even another hard-shelled lobster discovers its hiding place during this window, it will be mercilessly torn to pieces and devoured without a fight. During this terrifying period of absolute vulnerability, the soft lobster aggressively drinks in even more seawater, expanding its new, pliable shell like a balloon. It stretches the soft armor to a size roughly 20% larger than its previous body. Only then, once the maximum size is reached, does the creature begin to extract raw calcium from the ocean water, slowly, methodically hardening the new shell until it becomes a rigid, impenetrable fortress once again. The lobster has survived. It has traded its safety for size, emerging from the darkness larger, stronger, and ready to dominate the reef once more. This brutal, violent cycle of molting is the ultimate paradox of the lobster's existence. Its cells refuse to age, granting it the biological potential to live forever. But the relentless, unyielding physics of its own growth ensure that true immortality is impossible. As the lobster survives decade after decade, growing from the size of a human hand to the size of a small dog, and perhaps even larger, the physics of the molt become exponentially more demanding. To pull a massive, 40-pound body out of a thick, heavily calcified shell requires a catastrophic amount of metabolic energy. Eventually, after perhaps 50, 80, or over 100 years of life, a breaking point is reached. The giant, ancient lobster, still perfectly healthy on a cellular level, simply lacks the raw muscular energy required to break open its massive shell and survive the extraction. When that day comes, the creature realizes that the molt is impossible. It stops trying. It remains inside its heavy, ancient armor, but its cells, fueled by the relentless telomerase, continue to divide. They continue to grow. The immortal body slowly, agonizingly expands against the unbreakable cage of its own making. Eventually, the lobster is suffocated, crushed to death from the inside out by its own unstoppable biology. It is not killed by the slow decay of old age, but by the sheer, tragic weight of its own endless vitality. But until that distant, inevitable day arrives, the lobster endures. As the sun sets far above the Atlantic, casting the deep reefs into total, pitch-black darkness, the nocturnal shift begins. The ancient lobster, its new shell hardened and heavily armed, steps out from beneath the stone ledge, its antennae whipped through the freezing currents. tasting the chemical whispers of a fresh kill drifting down from the surface. It raises its massive crusher claw, a weapon that has been shed and rebuilt dozens of times over a century of life. It begins its slow, deliberate march across the rocky seafloor. It does not race against the clock like the mammals and the fish that swim above it. It does not fear the passing of the years. In the freezing, crushing darkness of the deep ocean, the armored knight walks onward, carrying decades of history in its cells, locked in endless, solitary war against its own unbreakable shell. The coastal waters of the Indo-Pacific often present a landscape that, from above, seems deceptively simple, almost barren. When you leave the towering, chaotic architecture of the coral reef behind, the ocean floor flattens out into an immense, unbroken expanse of pale sand. This is a marine equivalent of a desert. It is a wide, shallow arena interrupted only by the occasional scattered rock, a broken shell, or an isolated, lonely patch of seagrass swaying helplessly in the tidal current. For the vast majority of marine life, this open terrain is an absolute nightmare. There are no dark crevices to squeeze into. There are no branching corals to hide behind. It is a landscape defined by complete, terrifying exposure. Any creature that dares to venture across these bright, sunlit flats is instantly visible against a pale backdrop, an easy target for sleek, fast-moving predators that constantly patrol the open water above. To survive out here, an animal typically needs either explosive, blinding speed to outrun its enemies or heavy, impenetrable armor to survive their teeth. But creeping slowly across the exposed sediment is a creature that possesses neither speed nor armor. It is incredibly soft, completely boneless, and looks remarkably fragile. At first glance, it is entirely unremarkable. A small, slender cephalopod with long, delicate arms trailing across the seabed like thin ribbons of silk. Its skin is painted in a muted, apologetic palette of dull browns and dusty creams, trying its best to blend into the shifting grains of sand. This is the mimic octopus, and while it may appear vulnerable in this vast, open gladiator arena, it is arguably the most untouchable animal on the entire sandy plain. It does not survive by outswimming its predators. It does not survive by fighting them. It survives by fundamentally rewriting its own identity, utilizing a strategy of dynamic, psychological warfare that borders on the supernatural. The mimic octopus is the ocean's absolute master of illusion, a living stage capable of projecting an ever-changing cast of terrifying disguises. To understand the sheer genius of this animal, you must first understand the biological canvas upon which it works. The skin of the mimic octopus is not simply a barrier against the water. It is a neurological marvel, a high-definition, three-dimensional display screen wired directly into the creature's brain. Beneath the incredibly thin surface of its skin lies an incredibly dense, complex network of millions of microscopic pigment sacs called chromatophores. Each individual chromatophore is essentially a tiny balloon filled with intense pigment, black, brown, orange, yellow, or red. These balloons are tethered to microscopic muscles, which are in turn connected directly to the octopus's nervous system. When the animal fires an electrical impulse, the muscles violently contract, stretching the balloon wide and instantly exposing the brilliant color within. When the muscles relax, the color vanishes into a microscopic dot. Lying just beneath these pigment sacs are additional layers of specialized cells called iridophores and leucophores, perfectly designed biological mirrors that can instantly reflect and manipulate incoming sunlight to create shimmering, metallic hues or blinding, pure whites. By coordinating this entire system in fractions of a second, the octopus can shift its coloration, its patterns, and even its physical texture faster than the human eye can blink. But the mimic octopus does not simply use its power to match the sand and hide. It uses it to act. Suddenly, a shadow glides ominously over the sunlit seafloor. A large, predatory fish, perhaps a snapper or a small shark, is patrolling the shallows, its eyes scanning the pale sand for any movement that might betray a meal. The mimic octopus is caught perfectly out in the open. There is no rock to dart under. Fleeing would trigger the predator's deeply ingrained chase instinct, resulting in a fatal, high-speed pursuit. The octopus stops. It does not run. Instead, its body begins a terrifying, instantaneous transformation. The muted, sandy colors vanish, replaced instantly by bold, incredibly aggressive, highly contrasting, alternating bands of dark black and pale white. The octopus rears up. It spreads its 8 long arms outward in an elaborate, symmetrical radial pattern, lifting them away from the sand and suspending them in the water column. Within 2 seconds, the soft, helpless cephalopod has completely disappeared. In its place floats what appears to be a massive, highly venomous lionfish. The lionfish is a creature universally recognized and deeply feared across the tropical oceans. Its body is adorned with long, delicate, feather-like spines that carry a necrotic, agonizing venom. For almost any predator, the striking, banded silhouette of a lionfish is the ultimate biological warning sign. Do not touch, or you will suffer. But the octopus does not just look like a lionfish. It becomes a lionfish. It perfectly mimics the behavior of the toxic predator. The octopus begins to undulate its arms slowly, rhythmically, perfectly imitating the arrogant, unhurried, graceful drifting motion of a lionfish hovering above a reef. The approaching predator hesitates. Its brain registers the bold stripes, the splayed spines, the confident, slow movement. The illusion is flawless. The predator's instinct for self-preservation overrides its hunger. Unwilling to risk a mouthful of agonizing venom, the large fish turned away and swims off into blue. The bluff has worked. The octopus immediately drops the act. The stripes vanish, the arms collapse, and the creature resumes its quiet, creeping journey across the sand. But the ocean is unpredictable, and a single disguise is never enough. 10 minutes later, a different threat approaches. This time, it is a massive, aggressive damselfish, a territorial brute known for relentlessly attacking smaller invertebrates. The damselfish is not intimidated by lionfish. In fact, some larger fish actively hunt them. If the octopus attempts a lionfish illusion now, it might be called on its bluff and devoured. The octopus instantly assesses the specific identity of the new threat, and it changes the script entirely. This time, the octopus violently shoves 6 of its 8 arms straight down into the soft sediment, burying them completely out of sight. It leaves only 2 arms exposed, stretching them tightly together and pointing them straight backward. The rounded mantle of its head flattens out, elongating its body into a slender, continuous, rope-like shape. Instantly, intense ripples of contrasting color, stark blacks, bright yellows, and brilliant whites, flash across its skin in vertical bands. The octopus launches itself just inches above the seabed and begins to swim, but not with the typical pulsing jet propulsion of a squid or an octopus. Instead, it moves with a rigid, S-shaped, sinuous undulation. It is no longer an octopus. It is no longer a lionfish. It is now perfectly impersonating a highly lethal, highly aggressive banded sea snake. Sea snakes are the undisputed terrors of the shallow, sandy flats. They are reptiles armed with neurotoxic venom, so potent it rivals the deadliest snakes on land. Their bite brings swift, complete paralysis and death. Almost nothing in the ocean dares to intentionally attack a sea snake. As the aggressive damselfish charges in, it suddenly finds itself face to face with the undulating, banded body of an apex killer. The fish violently backpedals, its fins churning the water in panic, and flees the area as fast as it can swim. Once again, the Phantom of the Flats has manipulated the deep-seated psychological fears of its enemy to survive. This dynamic, fluid impersonation requires a level of physical and neurological coordination that defies belief. It is not enough to simply change color. The mimic octopus must alter its posture, its swimming mechanics, and its entire behavioral profile to match an animal it has no biological relation to. It must know exactly which predator fears which disguise. It must seamlessly transition from a hovering, radial fish to a slithering, elongated reptile, and it must do it in the blink of an eye. How does a creature without bones pull off such theatrical mastery? The secret lies in the bizarre architecture of the octopus's nervous system. In vertebrates like humans, the vast majority of our neurons are centralized in our brain, which sits in our skull and dictates orders to our passive limbs. The octopus is built entirely differently. It has a central brain, yes, but a massive 2/3 of its neurons are not in its head at all. They are distributed outward, embedded directly down the lengths of its 8 arms. In a very real sense, the arms of the octopus possess their own independent intelligence. When the central brain perceives a threat and decides on a disguise, become the sea snake, it does not need to consciously micromanage the exact angle, color, and movement of every single suction cup and muscle fiber. It issues a broad command, and the highly intelligent, decentralized neural networks within the arms themselves execute the complex mechanics. They instantly coordinate the precise posture, the rippling skin patterns, and the slithering motion locally. The result is a transformation so fluid, so perfectly synchronized, that it appears magical. But the mimic octopus does not just use its theatrical talents for defense. It is also an opportunistic, highly cunning predator, and it uses its illusions to manipulate its prey just as effectively as it manipulates its enemies. As the octopus continues its trek, it spots a small, delicious crab scuttling near a patch of broken shells. If the octopus charges, the crab will instantly recognize the shape of an 8-armed predator and vanish into the sand. The octopus needs to close the distance without triggering the crab's alarm. The octopus flattens its soft body completely flush against the seabed. It spreads its arms outward, pressing them together to form a wide, flat, continuous teardrop shape. The bold stripes and bands disappear. The skin instantly adopts a highly complex, mottled pattern of pale sand, dark grit, and broken shell fragments. Even the texture of its skin changes, rising in tiny bumps to perfectly mimic the rough, uneven surface of the seafloor. The octopus has become a flatfish, like a flounder or a sole. Flounders are incredibly common on the sandy flats. They are bottom-dwelling fish that spend their lives pressed against the sand. And to a crab, a passing flounder is a harmless, everyday sight. The mimic octopus, perfectly maintaining its flattened, leaf-like shape and its mottled camouflage, begins to glide slowly, innocently over the sand, moving with the exact undulating, rippling edge motion of a swimming flatfish. The crab watches the flatfish approach and dismisses it as a non-threat. It continues foraging, entirely unbothered. The octopus glides closer and closer, maintaining the absolute perfection of the illusion until it is directly over the crab. In a flash of violence, the flatfish illusion breaks. The arms explode outward. The suction cups lock onto the terrified crustacean, and the crab is dragged beneath the webbed canopy of the octopus to be consumed by its sharp, parrot-like beak. The ultimate ambush, executed through total psychological deception. This vast repertoire of disguises, the venomous lionfish, the lethal sea snake, the harmless flatfish, and perhaps dozens of other subtle impersonations that humans have not yet fully decoded, reveals a profound evolutionary truth. In the brutal, unforgiving environment of the open sand flats, where there is no physical shelter to be found, evolution was forced to find a different path. It could not provide the octopus with a heavy, cumbersome shell that would limit its mobility. It could not provide it with the crushing jaws of a shark. Instead, it provided the octopus with the ultimate weapon: extreme, unyielding cognitive and physical flexibility. It turned the animal's body into a constantly shifting illusion, a living lie that perfectly exploits the hardwired instincts and fears of every other creature on the reef. The mimic octopus thrives precisely because it understands how the rest of the ocean perceive the world, and it uses that perception against them. As the long, harsh shadows of the late afternoon begin to stretch across the sandy plain, the daily chaos of the coastal waters begins to settle. The mimic octopus reaches a small, quiet depression in the sand. Its long arms fold inward, pulling tightly against its body. The brilliant, shifting colors of the day, the bold warning stripes, the venomous bands, the mottled flatfish disguises, all fade away, melting back into the dull, quiet, muted tones of the ocean floor. Within seconds, the creature is entirely indistinguishable from the grains of sand that surround it. To a passing fish, to a soaring seabird, or to a diving human, there is absolutely nothing there, just an empty, barren stretch of the Indo-Pacific seabed. The master disguise, the greatest act of the ocean has ever produced, takes its final bow and simply vanishes, leaving behind only the faint, impossible impression that the sand itself had briefly, violently come alive. Along the quiet, sunlit margins of tropical coral reef, the underwater landscape undergoes a dramatic and unforgiving transition. The towering, brightly colored spires of living coral, teeming with the chaotic, vibrant energy of thousands of darting fish, abruptly give way to something far more desolate. This is the rubble zone. It is a vast, sloping graveyard of broken limestone, weather-beaten shells, and pale, lifeless sediment scattered across the ocean floor. Sunlight filters down to the shallow water in shifting, hypnotic ribbons, illuminating a terrain that feels defined entirely by its stillness. There are no branching corals to hide behind here. There are no dark caves to retreat into. To the casual observer, this fragmented landscape appears almost entirely devoid of life. For the vast majority of marine animals, this exposed environment presents an absolute, terrifying disadvantage. In the ocean, survival is a game of visual recognition. Apex predators, the sleek reef sharks, the massive groupers, the lightning-fast trevally, patrol these waters constantly, their eyes hardwired to detect the slightest anomaly. They scan the seafloor for the distinct silhouette of a fleeing fish, the contrasting color of a misplaced shell, or the sudden, erratic twitch of a desperate prey item trying to find cover. In this world, movement is a beacon, and visibility is a death sentence. But what if an animal could perfectly invert that logic? What if it could take the sheer, exposed vulnerability of the rubble zone and weaponize it, resting completely exposed on the broken stones, hiding in absolute, brazen plain sight, is an animal that has turned stillness into the ultimate evolutionary weapon. You could swim inches above it, you could stare directly at it, and your brain would simply refuse to register its existence. Nestled perfectly among the scattered debris is a stonefish, a predator so flawlessly, so completely disguised that it blurs the line between biology and geology. To call the stonefish camouflage is a profound understatement. Camouflage implies that an animal is merely trying to blend into a background. The stonefish does not blend in. It is an architectural forgery of the seafloor itself. Its body has been sculpted by millions of years of ruthless natural selection into an exact, three-dimensional replica of a heavily encrusted, algae-covered rock. Its skin is a masterpiece of textural deception. It is devoid of the smooth hydrodynamic scales that characterize almost every other fish in the sea. Instead, the stonefish is covered in a highly irregular, coarse, warty epidermis. This skin is heavily mottled with subdued, chaotic patches of muddy brown, dull gray, and sickly green, perfectly mirroring the exact tones of dead coral and accumulated sediment. But the illusion goes even further. The stonefish actually allows real, living marine organisms to colonize its body. Microscopic algae, tiny sponges, and actual physical debris from the surrounding water column settle and grow directly on its skin, completing a disguise so absolute that it defies visual detection. Even the animal's face has been erased by evolution. Its eyes, which in other fish are prominent and reflective, are deeply recessed into cavernous, bony pits on the top of its skull. They sit perfectly flush with the irregular surface of its body, ensuring they cast no shadow and break no outline. Its pectoral fins, rather than being used for swimming, are splayed outward and pressed firmly against the seabed, acting as physical anchors to prevent the ocean currents from rocking its body and betraying its presence. The stonefish does not swim. It does not actively hunt. It does not chase. It is a practitioner of extreme, uncompromising metabolic asceticism. It simply settles onto the rubble, becomes a stone, and waits. This strategy of absolute stillness is an exercise in profound patience and supreme energy conservation. While the sleek predators of the open water must constantly burn massive amounts of calories to chase down their meals, the stonefish lets the ocean bring the meal to its doorstep. It can sit in the exact same spot, utterly motionless, for days at a time, entirely unbothered by the shifting tides or the passing shadows of larger threats. It watches the water column above with a cold, calculating patience, its recessed eyes tracking the movements of the tiny, unsuspecting inhabitants of the reef. Above the rubble, the water is alive with small, busy creatures. Juvenile wrasses dart nervously between the rocks, searching for microscopic crustaceans. Tiny shrimp briefly emerge from beneath broken shells before retreating at the slightest shift in current. Among these foragers swims a young, brightly colored damselfish. It flits erratically through the water, its attention focused entirely on finding a patch of edible algae growing on the limestone debris. The damselfish spots a promising, algae-covered mound of rock on the seabed. It drops down from the water column, hovering just inches above the rough, warty surface. From the perspective of the damselfish, there is absolutely no indication of danger. The texture of the rock is perfect, The color is identical to the surrounding seabed. There is no electrical pulse, no shifting gill cover, no movement whatsoever suggests that this mound of stone is anything other than dead earth. The damselfish dips its head, opening its small mouth to peck at the algae. It has crossed the invisible threshold. What happens next is an act of biomechanical violence so astonishingly fast that it breaks the boundaries of fluid dynamics. For days, the stonefish has been a statue. Now, in a fraction of a millisecond, it becomes a localized black hole. The stonefish does not lunge forward to bite the damselfish. Biting takes too much time, and pushing the body forward to the dense medium of water creates a pressure wave that would alert the prey, giving it a split second to dart away. Instead, the stonefish relies on the devastating physics of negative pressure. Hidden within the rough, rocky facade of its face is a highly specialized, heavily modified skull. In an instant, the stonefish violently drops its lower jaw while simultaneously flaring out the bony plates covering its gills. This sudden, massive expansion of its internal oral cavity creates an instantaneous, catastrophic drop in water pressure right in front of its face. A powerful, inescapable hydrodynamic vacuum is formed. The surrounding water, carrying completely oblivious damselfish, is violently sucked inward. The fish has absolutely no time to process the event. There is no moment of panic, no attempt to flee. In less time than it takes a human eye to blink, less time than it takes a nerve impulse to travel from the damselfish's eye to its brain, it is pulled directly into the cavernous, waiting mouth of the predator and swallowed entirely whole. The jaws snap shut with a sickening thud. The gills flush out the excess water. The entire strike, from the initial unhinging of the jaw to the final, fatal trap, unfolds in roughly 15 milliseconds. The surrounding water barely ripples. The suspended sand doesn't even have time to settle. To anyone watching, the damselfish simply cease to exist, vanishing into thin air, while the algae-covered rock on the seafloor appears to have never moved at all. The stonefish immediately returns to its state of absolute, frozen inertia, its stomach now full, its illusion entirely unbroken. But the sheer speed and efficiency of its ambush is not the reason the stonefish commands such deep, universal terror across the Indo-Pacific. Its terrifying reputation is born of a completely different biological adaptation. Sitting exposed on the open seabed is a high-risk gamble. While its perfect camouflage hides it from the eyes of passing prey, it also hides it from the eyes of massive, heavy creatures that share the reef. A wandering sea turtle, a heavy, bottom-feeding nurse shark, or the clumsy, crushing weight a human foot could easily step on or bite into the motionless fish by sheer accident. If your entire survival strategy relies on refusing to move even when a massive object approaches, you must possess an absolute, uncompromising deterrent. You must ensure that if you are touched, the aggressor suffers a consequence so severe, so immediately agonizing, that it will never make the mistake again. Running along the ridge of the stonefish's back, buried perfectly flush with the warty, irregular surface of its skin, is a row of 13 stout, heavily calcified dorsal spines. When the fish is resting undisturbed, these spines are laid flat, angled slightly backward, completely invisible within the architectural forgery of its body. But these are not ordinary fins. They are the core components of the most lethal, highly evolved venom delivery system found in any marine environment on Earth. Each of these 13 spines functions exactly like a heavy-duty, biological hypodermic needle. They are sharp enough to easily pierce through the thick, rubbery neoprene of a diver's wetsuit, through leather, and deep into bone. At the base of every single spine, safely encased within the muscular tissue of the fish's back, are 2 massive venom glands. This weapon system requires absolutely no conscious thought from the stonefish. It does not need to decide to sting. It does not need to actively pump the venom. The entire mechanism is an elegant, terrifyingly simple, pressure-activated trap. If a heavy predator or a misplaced human foot presses down onto the back of the stonefish, the flesh around the dorsal ridge is pushed downward, instantly exposing the needle-sharp tips of the spines. The sheer physical weight of the attacker drives the rigid spines deep into its own flesh. As the spine penetrates, the downward pressure simultaneously compresses the venom glands at the base. The glands violently rupture, forcing a highly concentrated payload of venom up through specialized, hollow grooves running the entire length of the spine, injecting the toxin directly, deep into the victim's wound. The heavier the pressure, the deeper the spine goes, and the larger the dose of venom injected. It is an automatic, flawlessly designed mechanical punishment, and the venom itself is a masterpiece of biochemical horror. It is a thick, milky cocktail of highly complex proteins, powerful enzymes, and devastating neurotoxins. The moment it enters the bloodstream, it unleashes a catastrophic, multi-system biological assault. In smaller marine predators, the venom instantly attacks the nervous system, aggressively blocking the electrical signals between nerves and muscles. It causes rapid, total paralysis, followed almost immediately by cardiovascular collapse and death. But for larger animals, including humans, the venom is specifically engineered to produce something far more effective than immediate death. It produces pure, unadulterated agony. The toxins possess severely cytolytic properties, meaning they immediately begin to attack and destroy the cellular walls of the surrounding tissue, causing massive, instantaneous cellular death and extreme, localized swelling. It forcefully overrides the pain receptors in the nervous system, sending absolute, blinding signals of trauma to the brain. Medical literature and survivor accounts describe the pain of a stonefish sting as the most excruciating, absolute torment a human body can experience without losing consciousness. The pain radiates violently outward from the puncture wound, moving rapidly up the limb, causing intense muscle spasms, extreme respiratory distress, and wild, dangerous fluctuations in blood pressure. Without immediate, specialized medical intervention and the administration of specific anti-venom, the tissue necrosis can be so severe that it requires amputation, and the sheer shock to the cardiovascular system can be fatal. Yet, despite harboring this weapon of mass biological destruction, the stonefish is not a monster. It is not an aggressive killer. It never uses its venom to hunt, and it never actively attacks. The venom is purely, strictly defensive, a chemical shield necessitated by its total commitment to stillness. The stonefish does not want to sting. It simply wants to be left completely alone, ignored by the world, disguised as a piece of dead coral. The existence of such a potent weapon plays a fascinating, invisible role in the broader ecology of the coral reef. In the animal kingdom, pain is a highly effective teacher. The apex predators of the reef, the large sharks, the massive groupers, the moray eels, possess long memories. Those that have brushed against a stonefish and survived the excruciating encounter quickly learn a vital lesson. They learn to view the barren rubble zones with deep suspicion. They learn that some rocks are not rocks at all, and that the penalty for carelessness is unbearable pain. Through this learned avoidance, the stonefish quietly, indirectly shapes the behavior of the ocean's greatest hunters. It keeps them wary. It prevents them from carelessly dominating the shallow flats, inadvertently providing a small measure of safety to the other, non-venomous creatures that forage in rubble. Without ever swimming a single yard in pursuit, without ever baring a tooth or snapping a jaw in aggression, the motionless stonefish exerts a powerful, unseen influence over the entire hierarchy of the reef. As the long, intense day of the tropics begins to fade, the brilliant, piercing sunlight filtering through the shallow water shifts into a deeper, cooler blue. The shadows cast by the limestone debris grow long, stretching out across the pale sediment. The frantic, high-speed daytime activity of the reef begins to wind down, transitioning into slower, more cautious rhythm of the nocturnal shift. Throughout it all, the stonefish remains exactly where it was. It has not moved a single inch since the morning. Its recessed eyes continue to stare blankly up into the darkening water column. Its warty, algae-covered skin blends seamlessly into the advancing shadows. It is the absolute embodiment of a biological paradox. It appears to be the most inert, lifeless, helpless object on the seafloor. Yet, contained within its rigid, motionless body is one of the fastest, most violently efficient feeding mechanisms in the natural world, backed by a chemical arsenal of unimaginable, terrifying power. For the countless fish drifting lazily above the seabed, the rocks below appear familiar, safe, and entirely mundane. They pass by in the darkening water, completely unaware that they are swimming inches above a predator that has mastered the ultimate evolutionary illusion. The stonefish does not stalk. It does not pursue. It simply waits, perfectly erasing the world around it, proving that in the ruthless, high-stakes theater of the ocean, The most dangerous thing you can encounter is often the thing you never saw at all. Leave behind the intricate, sheltering architecture of the coral reefs. Leave behind the sun-drenched coastal shallows and the tangled, swaying forests of kelp. Travel outward past the continental shelf into a realm that covers more than half of the planet's surface, yet remains the most alien environment on Earth, the open ocean. This is a pelagic zone, a vast, three-dimensional wilderness of water. There are no walls here, no seabed to rest upon, no rocks to hide beneath, and no physical boundaries to mark territory. It is a world of pure, suspended exposure. In this endless, featureless blue void, survival is stripped down to its most absolute fundamentals. You cannot outlast your enemies by hiding in a crevice, because there are no crevices. You cannot blend into the sand, because the bottom is miles below. In the open ocean, life is an unforgiving equation of speed, sensory perfection, and the ability to manipulate the water itself as both a highway and a shield. And gliding effortlessly through this mid-water realm, perfectly adapted to a world without edges, is an animal that has abandoned the traditional rules of marine biology. It is not a fish. It does not swim with the rhythmic sweeping of a tail. It is a cephalopod, a creature whose entire body has been ruthlessly engineered into a biological machine for explosive acceleration, high-definition optical communication, and lightning-fast predatory strikes. This is a squid. Watch it drift in the twilight zone, that mysterious layer of the ocean where the sun's rays are stretched thin, turning the water into a deep, pervasive indigo. At rest, the squid appears almost impossibly elegant. Its body is dominated by the mantle, a long, torpedo-shaped muscular sac that encloses its internal organs. Two triangular fins undulate smoothly along the sides of the mantle, providing gentle, stabilizing lift, allowing the animal to hover weightlessly in the water column. It looks calm, completely at peace in the immense pressure of the deep, but this calm exterior conceals an engine of violent, staggering power. The squid is the inventor of biological jet propulsion. In fish, respiration and locomotion are two separate systems. The gills breathe, the tail swims. For the squid, these functions are beautifully, violently combined into a single mechanism. The thick, muscular walls of the mantle are designed to expand, drawing surrounding seawater deep into the internal cavity, washing over the gills to extract vital oxygen. But when the squid needs to move, the mantle ceases to be a lung and becomes a pressurized combustion chamber. The powerful muscles of the mantle wall violently contract, instantly squeezing the internal cavity. The water cannot escape the way it came in. Instead, it is forced under massive pressure out through a narrow, highly articulated muscular tube located just beneath the squid's eyes, known as a funnel or siphon. This incredibly fast expulsion of water creates a massive jet of thrust, propelling the squid in the opposite direction with the exact same physical principles used by a modern fighter jet. With a single explosive pulse of its mantle, the squid can launch its body several meters in an instant. But the true genius of the system is not just its raw speed. It is its unparalleled, chaotic maneuverability. The funnel is entirely flexible. The squid can instantly point it forward, backward, or sharply to side. While pursuing shark or tuna is locked into the relatively wide, sweeping, turning radius dictated by its rigid spine and tail, the squid can change its trajectory at physically impossible angles. It can blast forward, instantly reverse thrust to shoot backward, and pivot on a dime, turning a high-speed chase into a dizzying, three-dimensional dogfight. Yet, in the dim, twilight waters of the open ocean, speed is only half the equation. The other half is invisibility. And here, the squid employs technology that borders on the miraculous. It does not merely change color. Operates as a living, breathing, high-definition display screen. Just beneath the incredibly smooth surface of the squid's skin lies an intricate, densely packed network of millions of chromatophores. These are microscopic, elastic sacs filled with intense, concentrated pigments, deep reds, brilliant yellows, dark browns, and blacks. Each individual pigment sac is tethered to a microscopic ring of radial muscles, which are wired directly, physically, into the squid's highly advanced brain. When the squid's brain fires an electrical impulse, the microscopic muscles instantly contract, violently stretching the pigment sac wide open and flashing its color across the skin. When the impulse stops, The muscles relax, the sac shrinks to an invisible dot, and the color vanishes. Because this system is neurologically controlled, rather than hormonally controlled like in many other animals, the speed of the color change is staggering. The squid can send rolling, hypnotic waves of color cascading down the length of its mantle in fractions of a second. It can flash stark white to reflect a faint light from above, or instantly turn blood red, a color that is physically invisible in the deep ocean, rendering the animal effectively black and perfectly cloaked in the shadows. But these flashing displays are not merely for camouflage. In the vast, open water, there are complex optical language. When two squid encounter each other in the void, their skin erupts in a frantic, high-speed dialogue of flashing patterns, signaling aggression, territorial dominance, or complex mating readiness. They speak to each other in a language of pure light and color, broadcasting their intentions across the indigo expanse. Suddenly, the squid's skin goes completely, eerily pale. A disturbance has rippled through the water column. Dozens of yards away, a lone lanternfish is darting erratically, its tiny bioluminescent organs flickering as it searches for plankton. To hunt in this shadowy realm, a predator needs optical equipment of the highest possible caliber. The squid possesses some of the most advanced, massively proportioned eyes in the entire animal kingdom. Relative to its body size, its eyes are gigantic, equipped with massive, spherical lenses specifically evolved to capture every single stray photon of light available in the deep ocean. These eyes do not just see silhouettes. They process high-resolution, sharply focused images, giving the squid absolute visual dominance over its environment. The squid locks onto the flickering lanternfish. Its posture shifts. The undulating fins lock firmly against the sides of the mantle to reduce drag. The funnel angles perfectly backward. The squid pulses, a silent, ghostly missile sliding to the dark water, rapidly closing the distance. Extending from the front of the squid's head is a dense cluster of appendages, but they are not all created equal. 8 of these are relatively short, heavily muscled arms, lined on their inner surfaces with hundreds of powerful, toothed suction cups. But hidden securely within this cluster, tightly coiled and waiting under immense muscular tension, are 2 highly specialized, heavily elongated feeding tentacles. These are the squid's ballistic weapons. The squid glides to within striking distance. The lanternfish is still completely oblivious. In a biological explosion of speed that is almost impossible to track with the human eye, the squid fires. The 2 massive feeding tentacles shoot outward, propelled by the violent contraction of circular muscles that squeeze them out like toothpaste from a tube, launching them forward at terminal velocity. At the very tips of these long, elastic cables are flattened, club-like pads, armed with the largest, sharpest, and most powerful suckers on the animal's body. The clubs slam into the lanternfish. The toothed suckers bite deep into the scales, locking onto the prey with inescapable force. Instantly, the elastic muscles snap in reverse. The tentacles recoil, violently ripping the struggling fish backward out of the water column and dragging it directly into the waiting embrace of the 8 shorter arms. The arms wrap around the prey, forming a suffocating, inescapable cage of muscle and suction. At the very center of this writhing mass of arms lies the squid's mouth. It does not have teeth like a fish. Instead, it possesses a massive razor-sharp beak, structurally identical to that of a parrot, composed of incredibly dense, hardened chitin. The beak opens, powered by crushing jaw muscles, and effortlessly slices through the spine, flesh, and bone of the lanternfish. The kill is swift, clinical, and completely devastating. Within seconds, the meal is consumed, and the squid returns to its quiet, hovering drift, a ripple of dark red flushing down its mantle to signal its satisfaction. This is a perfection of the midwater squid. But the design of this biological machine is so successful, so flawlessly adapted to the physics of the open ocean, that evolution did not stop here. It took this exact blueprint and pushed it to the absolute, terrifying extreme. Sink deeper, leave the twilight zone behind, and plunge down into the bathypelagic zone, the true abyss. 3,000 feet, 5,000 feet. Down here, the temperature hovers just above freezing. The pressure is crushing, capable of imploding steel. There's absolutely no sunlight. The water is a thick, inky, eternal black, pierced only by the occasional, alien flashes of bioluminescence. Here, drifting in the lightless void, lives a titan of the cephalopod world, the giant squid. For centuries, this creature existed only in the terrifying legends of sailors, spoken of in hushed tones as the kraken, a monster capable of dragging entire ships down to the deep. Today, we know it as a flesh-and-blood reality, an animal that can reach staggering lengths of over 40 feet, with eyes the size of dinner plates, the largest eyes of any living animal, designed to detect the faintest, ghostly glow of bioluminescence in the pitch black. Down in the abyss, the hunting strategies are the same, but the scale is the stuff of nightmares. The giant squid's feeding tentacles can stretch out for dozens of feet into the dark, armed with suckers lined with jagged, razor-sharp rings of chitin. When it fires these tentacles, it is reaching out into blackness to snatch prey from distances that seem impossible. But the giant squid is not the uncontested king of the deep. It shares this lightless arena with the ultimate apex predator of the abyss, the sperm whale. These massive, air-breathing mammals dive thousands of feet into freezing dark specifically to hunt giant squid. The battles that take place down in the abyss are titanic. Violent clashes of leviathans that no human eye has ever witnessed directly. The sperm whale descends, unleashing a barrage of incredibly powerful, focused sonar clicks, using sound to physically locate the massive squid in the absolute darkness. When the whale closes in, the squid fights back with everything it has. It fires its jet propulsion, desperately trying to evade the massive jaws. It lashes out with its colossal arms and tentacles, wrapping them around the whale's head, fighting for its life. We know these desperate, violent struggles occur because of the silent, undeniable testimony written on the bodies of the whales. When sperm whales return to the surface to breathe, their massive, block-like heads are frequently covered in dozens of deep, circular, jagged scars, the permanent branding marks left behind by the desperate, tearing suckers of the giant squid fighting to avoid the crushing jaws of the mammal. Returning to the twilight zone, the smaller midwater squid continues its patrol. It is not a giant, but it faces its own daily terrors. A shadow detaches itself from the blue gloom above. It is an oceanic white-tipped shark, a relentless, highly efficient cruiser of the open water. The shark's sensory systems have locked onto the electrical impulses of the squid, and it banks sharply, accelerating into a predatory dive. The squid registers the massive, approaching threat. It does not attempt to fight. It knows that in a straight-line sprint, the shark's powerful tail might eventually run it down. It must use deception. As the shark opens its jaws for the killing strike, the squid executes its ultimate defensive maneuver. Deep within its internal cavity is a specialized sac filled with a dense, viscous liquid comprised of melanin and mucus. With a violent contraction of its funnel, the squid ejects a massive, concentrated burst of this ink directly into the water. But this is not just a smokescreen. The thick mucus in the ink holds the dark pigment together in the water column. For a few crucial seconds, the ink cloud forms a cohesive, suspended mass that is roughly the exact same size and shape as the squid itself. It is a biological decoy, a pseudomorph, a phantom squid. Simultaneously, the moment the ink is fired, the squid instantly flushes every single chromatophore on its body, turning completely, perfectly transparent. And with a massive, explosive pulse of its jet, it shoots backward at blinding speed. The shark charges a dark, squid-shaped mass of ink, its jaws snapping shut on nothing but bitter, confusing water. The decoy disperses into a cloud, momentarily blinding the shark's vision and overwhelming its olfactory senses. By the time the water clears, the shark is alone. The real squid is 50 yards away, completely invisible, hovering silently in the blue void. The open ocean remains vast, empty, and merciless. It is a place that demands absolute perfection from the animals that dare to live suspended within it. The squid is the embodiment of that perfection. It is a creature that breathes by moving and moves by breathing. It is a living, high-definition optical illusion, capable of speaking in color and vanishing into the shadows. Its body is a fusion of rocketry, optics, and deadly, spring-loaded mechanics. As the deep currents push through the featureless twilight, the squid pulses onward, a silent, biological jet fighter patrolling the boundless three-dimensional wilderness of the sea. swim to the very edge of the coral reef, to the exact boundary line where the sun-drenched, chaotic metropolis of the shallows abruptly comes to an end. This is a drop-off. It is a dramatic, terrifying transition zone, an underwater cliff face with a vibrant, protective labyrinth of limestone and branching coral simply plummets away into the deep, bottomless blue of the open ocean. Behind you lies a world of hiding places, of narrow crevices, of shadows and shelter. Ahead of you stretches a vast, unforgiving emptiness. It is a corridor of extreme tension, a borderland between two entirely different dimensions of survival. And it is right here, suspended perfectly motionless in the shifting currents of this boundary line, that you will find a predator engineered for a single, terrifying purpose: explosive, uncompromising violence. Look closely into the blue void just beyond the reef's edge. At first, you might see nothing but the sunbeams descending like massive, glowing columns through the water, illuminating the drifting dust of microscopic plankton. But then, a shape begins to resolve in the filtered light. It is long, sleek, and perfectly still. It glimmers faintly, a shimmering cylinder of silver and muted blue hovering weightlessly in the water column. It appears entirely relaxed, exerting absolutely no visible effort, holding its position against the coastal current with only the most imperceptible twitches of its fins. This is the great Barracuda. It is not an animal built for the long, grueling migrations of sea turtle, nor is it designed for the complex, psychological warfare of an octopus. The Barracuda is a creature stripped of all evolutionary excess. Its anatomy is a masterclass in localized lethal physics. It is, in the truest sense of the term, a living biological missile. Observe the architecture of its body. It is a perfect, elongated torpedo, an unbroken, streamlined wedge designed to part the dense, heavy medium of water with the absolute minimum of hydrodynamic drag. It tapers flawlessly from a sharply pointed, arrow-like snout down to a massive, deeply forked tail. But the true secret of its lethality lies hidden beneath its skin, within the dense, tightly packed musculature that runs along its flanks. In the ocean, predators are generally divided into two categories: the marathon runners and the sprinters. Pelagic hunters like tuna and some sharks are packed with dark, oxygen-rich, slow-twitch muscle fibers, allowing them to swim continuously at high speeds for hours, running down their prey through sheer, unyielding endurance. The Barracuda, however, is the ultimate sprinter. Its body is heavily dominated by white, fast-twitch muscle fibers. These muscles are not designed for stamina. If forced into a long, sustained chase, a barracuda will rapidly exhaust itself. Instead, these muscles are designed for one thing: instant catastrophic, explosive acceleration. Because it lacks the endurance to chase prey across the open ocean, the barracuda must conserve its energy with absolute discipline. This is why it hovers at the edge of the drop-off, seemingly locked in a state of suspended animation. It does not actively patrol. It does not blindly burn calories. It simply drifts in the silent corridor, its large, top-mounted eyes providing a massive, wide-angle field of vision. It watches the frantic, high-energy activity of the reef behind it, and it watches the endless blue expanse ahead of it, waiting with cold, terrifying patience for the exact, perfect moment to unleash its stored kinetic energy. To hunt successfully in this exposed, brightly lit environment, the barracuda must overcome a massive disadvantage. It has no rocks to hide behind. It cannot bury itself in the sand like a flatfish or a stingray. It is a massive, incredibly dangerous predator hovering in plain sight. If a school of small fish sees it clearly, they will never swim close enough for the ambush to work. To solve this, the barracuda employs a cloaking mechanism based entirely on the manipulation of light. Its long, slender body is covered in specialized, crystalline scales. These scales do not absorb light to blend in with a dark background. Instead, they operate as millions of microscopic mirrors. As the tropical sunlight strikes the barracuda, these scales scatter and reflect the light outward in brilliant, erratic flashes of silver. In the dynamic, chaotic environment of the reef edge, this optical strategy is sheer genius. The water here is already filled with millions of small, schooling fish, sardines, silversides, and baitfish, whose own silver scales constantly flash and glint as they turn synchronously in the sun. When a school of prey looks toward the hovering barracuda, their brains do not register the distinct, terrifying outline of a massive apex predator. Instead, the Barracuda's reflective armor creates intense optical confusion. The predator's flashing scales mimic the exact chaotic shimmering of the bait ball itself. To the prey, the Barracuda dissolves into the visual noise of the environment. It becomes nothing more than a trick of the light, a shifting, glittering anomaly in the water column that completely masks the lethal threat hidden within. A massive school of small fish sweeps out from the safety of the coral branches, venturing slightly over the drop-off to feed on the rich clouds of plankton drifting in the open current. They move as a single, highly coordinated liquid entity. Thousands of silver bodies turn, dive, and rise in perfect, synchronized harmony. This schooling behavior is a highly effective defense mechanism. It creates a swirling, confusing mass of targets that makes it almost impossible for a predator to lock its eyes onto a single, individual fish. If a hunter charges blindly into the center of the school, the fish simply part like a curtain, letting the predator rush through empty water before seamlessly reforming behind it. The Barracuda knows this. It does not move. It does not flinch. It holds its position in the current, becoming just another shimmer of light, and it watches. It is playing a game of absolute, uncompromising odds. It knows that in a school of 10,000 fish, perfect synchronization is impossible to maintain forever. Eventually, the formation will loosen. Eventually, the current will shift unpredictably. Eventually, a single, distracted fish will see a particularly large piece of plankton and break formation, drifting just a few inches too far from protective safety of the swirling mass. The Barracuda waits for that exact, fatal fraction of a second. A lone fish lags slightly behind the turning wall of silver. The distance between the predator and the prey is perhaps 20 feet. The strike is not a swim, it is a detonation. The heavy, fast-twitch muscles running down the Barracuda's flanks violently, simultaneously contract. The massive, deeply forked tail sweeps sharply to one side, gripping the dense water with incredible surface area, and throws the full weight of the animal forward. The acceleration is so violently explosive that the water around the predator seems to physically shatter. In less time than it takes a human heart to beat, the Barracuda crosses a 20-foot gap. It moves so fast that the human eye cannot track the physical motion of its body. It registers only as a sudden, silver blur, a localized lightning strike beneath the sea. The prey fish has absolutely no time to react. Its nervous system cannot even process the approaching threat before the attack is already over. As the biological missile reaches its target, the long, pointed jaws snap open. Here, the Barracuda reveals its most terrifying anatomical feature. While many fish possess rows of tiny, gripping teeth designed to swallow prey whole, the Barracuda's mouth is an arsenal of asymmetrical, deeply terrifying weaponry. Lining both the upper and lower jaws are long, completely unsheathed, dagger-like teeth. They are heavily pointed, incredibly sharp, and angled slightly backward. These are not teeth designed for grinding or holding. They are designed for catastrophic, flesh-shearing trauma. When the Barracuda strikes, it does not need to perfectly engulf the prey. If the strike is even slightly off-center, the jaws slam shut with immense, crushing force, and the daggers effortlessly slice through scales, muscle, and bone. A larger fish caught in this strike might simply be bitten entirely in half by the sheer, unyielding velocity of the impact combined with the razor-sharp teeth. The jaws snap shut around the stray fish. The prey is instantly pulverized and swallowed before the Barracuda has even finished its forward glide. The momentum from the explosive launch carries the predator several yards beyond the point of impact. And then, as quickly and violently as it began, the hunt is over. The Barracuda arrests its forward motion. Its fins flare out, catching the water like brakes. It slowly, smoothly turns its long body back into the current. Within seconds, it returns to its exact previous state of quiet, suspended animation. The silver scales shimmer in the sunlight. The long, predatory silhouette dissolves back into the optical noise of the reef edge. The living missile has fired, reloaded, and returned to the silo. But a life defined by such violent, high-speed impacts takes a massive physical toll, particularly on the predator's primary weapons. Biting through the dense, bony spines of reef fish at 30 or 40 miles per hour places immense, shattering mechanical stress on the Barracuda's dagger-like teeth. During these explosive strikes, teeth are frequently chipped, snapped cleanly off, or ripped entirely from the jawbone. If the barracuda had only a single set of teeth, a few weeks of hunting would leave it completely toothless, resulting in slow, inevitable starvation. To counter the extreme violence of its own lifestyle, the barracuda relies on a continuous, lifelong system of anatomical regeneration. Just beneath the gum line, hidden deep within the jawbone, lies a perpetual assembly line of fresh, razor-sharp teeth. Whenever a tooth is broken, worn down, or violently ripped out during a strike, the biological machinery immediately pushes a new, perfectly formed dagger upward to take its place. This continuous, relentless replacement cycle ensures that no matter how many times a missile is fired, no matter how much bone it shatters in its jaws, the barracuda is always armed with a completely pristine, lethal set of cutting tools, forever ready for the next ambush. While they are often solitary hunters, the reef edge frequently plays host to loose, intimidating aggregations of these predators. Sometimes, dozens of massive barracudas will gather in the same specific corridor where ocean currents aggressively sweep over the drop-off. They do not hunt cooperatively like a pod of dolphins or a pack of wolves. They do not communicate or coordinate their strikes. They simply hover together, suspended in the water column like a silent, heavily armed gang holding a strategic intersection. Their sheer, collective presence fundamentally alters the psychology and the architecture of the reef ecosystem. When a school of prey fish encounters a wall of hovering barracudas, panic sets in. The prey is forced into tighter, more stressful formations. They move more erratically, burning precious energy, and their heightened fear makes them significantly more prone to making the one fatal mistake of breaking formation. By simply existing at the edge of the drop-off, the barracudas exert massive, unseen gravitational pressure on the populations of the reef. They cull the weak, they punish the distracted, and they ensure that the dynamic equilibrium between predator and prey is ruthlessly maintained. As the tropical sun climbs to its absolute zenith, the water at the edge of the drop-off turns a brilliant, blinding sapphire. The chaotic, ceaseless energy of the coral reef behind them continues its frantic pace. But out here, suspended in the blue corridor, the barracudas do not participate in the frantic rush. They are the masters of the waiting game. They are the ultimate realization of biological physics, a flawless marriage of visual deception, raw, fast-twitch acceleration, and continuously regenerating weaponry. They hang weightless in the current, perfectly still, their crystalline scales throwing off random, confusing sparks of light. They watch the swirling clouds of silver fish with cold, unblinking eyes. They do not pursue. They do not waste energy. They simply drift in the silent void between safety and the abyss, waiting for the ocean to make a mistake. And when that mistake happens, the water will shatter, the daggers will strike, and the missile of the reef will prove, once again, that in the open ocean, speed is the ultimate, undeniable arbiter of life and death. Morning light spills across the surface of the coastal sea, transforming the water into a shifting, limitless mirror of pale gold and electric blue. Beneath this luminous, undulating ceiling, the underwater world awakens gradually, dictated by the ancient, daily circulation of the tides. Currents begin their steady push across sprawling limestone reefs, expansive seagrass meadows, and the deep, open channels that connect the sheltered, shallow coast to the chaotic, boundless ocean beyond. It is an ecosystem defined by its relentless, frantic energy. Massive schools of sardines gather in dense, trembling formations, their bodies flashing silver, whenever a solitary shaft of sunlight penetrates the surface. Heavily armored rays glide silently across the sandy flats in search of buried mollusks, their wings kicking up clouds of white sediment. Ancient leather-skinned sea turtles browse methodically through the tall, green leaves of the seagrass beds, entirely absorbed in their slow, grazing rhythm. Among this rich, wildly diverse, and deeply distracted ecosystem moves a group of animals whose mere presence fundamentally alters the rhythm and the psychology of the sea itself. They do not arrive as solitary, ambushed predators waiting in the shadows. They arrive as collective, a unified, deeply connected society, moving through the water in tight, flawless formations that suggest a level of coordination far beyond the limits of basic, hardwired instinct. A small pod of dolphins approaches from the deeper, darker water, Their streamlined, muscular bodies cut through the dense medium of the sea with a quiet, breathtaking efficiency. Their curved dorsal fins slice the surface simultaneously as they rise to breathe, exhaling in sharp, explosive bursts before descending once again into the submerged landscape below. Each animal maintains incredibly close proximity to the others, riding the hydrodynamic slipstreams created by their companions to conserve energy. They adjust their speed and direction in subtle, instantaneous responses to the group's collective movement. The choreography appears completely effortless, a fluid dance of marine physics. Yet, beneath this physical grace lies one of the most overwhelmingly complex, deeply mysterious social systems found anywhere in the natural world. To truly understand the dolphin, you must look past its speed and its physical power and look instead into the architecture of its mind. Dolphins possess brains that are almost terrifyingly large relative to their overall body size. When evolutionary biologists calculate the encephalization quotient, the ratio comparing the mass of the brain to the mass of the body across all animal species, dolphins consistently rank among the absolute highest in the natural world, standing shoulder to shoulder with the great apes and second only to humans. But the sheer size of the brain tells only a fraction of the story. The physical structure of the dolphin's brain reveals a profound capacity for high-level thought. Their cerebral cortex, the outer layer of the brain responsible for problem-solving, memory, and conscious thought, is subjected to a staggering degree of folding. It is heavily creased with deep convolutions, massively increasing the total surface area available for processing highly complex neurological information. Furthermore, they possess specialized brain cells known as spindle neurons, structures historically associated only with humans and elephants, linked directly to the processing of deep emotion, social empathy, and rapid judgment. This incredibly intricate, powerful neural architecture supports a lived experience that involves long-term memory, sophisticated learning, and a web of social interactions so complex we're only just beginning to decode them. As the pod glides through the bright coastal waters, they are not swimming blindly. Their brains are processing a torrent of sensory data, gathered through a biological technology that borders on a superpower. Dolphins perceive their vast, three-dimensional world not just through sight, but through sound. They rely heavily on echolocation, a highly advanced biological sonar system that allows them to literally see through the ocean by interpreting acoustic waves. Hidden within the dolphin's forehead is a specialized, fat-filled organ known as the melon. Below the blowhole, a complex system of nasal air sacs produces rapid, high-frequency clicks. The melon acts exactly like an acoustic lens, focusing these clicks into a highly directional, concentrated beam of sound energy that the dolphin projects forward through the water. Sound travels more than 4 times faster in water than it does in the air, creating a lightning-fast sensory network. When these projected sound waves encounter physical objects, a jagged coral structure, a hidden patch of sandy seabed, or the soft, trembling bodies of school fish, the sound waves bounce back. These returning echoes are captured not by the dolphin's ears, but by its lower jawbone, which is filled with specialized acoustic fat that channels the vibrations directly into the inner ear. By continuously analyzing precise timing, the pitch, and the returning intensity of these echoes, the dolphin's massive brain constructs a flawless, highly detailed, three-dimensional acoustic image of its surroundings. They can detect the exact size, shape, speed, and even the internal density of a target from hundreds of yards away. They can literally hear the swim bladders of fish hidden deep within the shadows of the reef. Through this invisible overlapping web of echolocation clicks, the pod identifies a dense, chaotic cluster of fish moving erratically along the outer edge of the seagrass meadow. It is a massive bait ball of sardines, forming a shifting, terrified cloud that reacts instantly to the approaching acoustic pressure. Many marine predators would simply charge into this bait ball, snapping their jaws blindly in a chaotic frenzy of raw hunger. But the dolphins rarely rely on brute force alone. Instead, they begin to organize. Their movements shift from a relaxed travel formation into a highly structured, tactical deployment that reveals a terrifying, chilling level of cognitive coordination. Without breaking stride, the pod fractures into specific, specialized roles. Several individuals aggressively accelerate, positioning themselves along the outer, seaward edge of the fish school, forming a living wall to block the sardines from escaping into the deep open ocean. Other dolphins dive deep toward the seabed, circling rapidly from below to push the bait ball upward toward the surface. The group moves in flawless unison, deliberately compressing the millions of fish into an increasingly tight, panicked, swirling sphere. They are actively herding their prey, guiding them relentlessly toward the shallow water of the reef flat, where all avenues of escape will be completely cut off. This coordinated, collective hunting strategy requires a level of tactical anticipation and mutual understanding rarely observed anywhere in the ocean. Every single dolphin appears to explicitly understand its specific role within the group's dynamic formation. They constantly adjust their positions, reacting not just to the frantic, unpredictable movements of prey, but anticipating the strategic maneuvers of their fellow hunters. The sardines attempt to violently flee, thousands of silver bodies flashing in panic, but every single path leads directly toward another dolphin, waiting strategically nearby, snapping its jaws just enough to force the fish back into the trap. As the school tightens under immense, crushing pressure, the dolphins do not simply gorge themselves simultaneously. They take turns. Individual dolphins dart forward into the compressed sphere, seizing several fish in a lightning-fast strike, before instantly returning to their precise positions on the perimeter to maintain the structural integrity of the hunting ring. It is a masterclass in lethal, disciplined cooperation, but such breathtaking coordination is completely impossible without a highly advanced system of communication. The ocean may seem silent to human ears, but beneath the surface, it is a deafening, chaotic symphony of acoustic information. Dolphins possess an extraordinary, incredibly varied repertoire of vocal signals that facilitate their complex social interactions. Their underwater conversations consist of a rapid-fire sequence of high-pitched whistles, guttural clicks, squawks, and deeply pulsed sounds that can carry across vast distances through the ocean's incredibly dense medium. Among these acoustic signals is a phenomenon that has stunned marine biologists: the signature whistle. Each individual dolphin develops a completely unique, highly specific pattern of sound within the first few months of its life. This signature whistle functions exactly like a human name. It is a distinct acoustic identity badge. Dolphins use these whistles to constantly broadcast their individual identity to the rest of the pod, allowing companions to recognize exactly who is swimming nearby, even when separated by miles of murky water or total darkness. When pods merge, or when individuals are separated during a chaotic hunt, they will frantically call out their own names and actively call the names of their specific friends and family members to reunite. This level of specific individual acoustic identity is the crucial neurological foundation that allows them to maintain deep, lifelong social bonds within highly fluid, constantly changing societies. The acoustic landscape surrounding the pod during a hunt is wildly animated. Rapid-fire clicks signal the focused echolocation pulses directed toward the fish, while a dense, overlapping network of signature whistles and instructional bursts ripples continuously through the water between pod members. They are actively talking to one another, coordinating the trap in real time. Beyond communication and cooperative hunting, dolphins routinely exhibit behaviors that reveal a capacity for abstract innovation, a level of problem-solving almost never seen among wild animals. In certain coastal regions of the world, where the ocean floor is dominated by rough, abrasive coral rubble and heavily armored, stinging organisms, some dolphins have developed a breathtaking technique involving the use of environmental tools. When searching for small, nutritious fish hiding deep beneath the loose, jagged sediment, a dolphin risks severely injuring the sensitive, highly innervated skin of its snout on sharp rocks or buried, venomous spines. To solve this ecological challenge, dolphins have been observed diving down, tearing large, cone-shaped marine sponges directly off the seabed and physically wearing them over the tips of their rostrums like protective, biological gloves. With the sponge securely in place, the dolphin can aggressively, fearlessly plow its snout deep into the sharp, abrasive rubble. As the dolphin sweeps the sponge across the bottom, terrified, concealed fish suddenly dart upward out of the sediment, revealing themselves to the waiting, protected hunter. This behavior is a monumental milestone of intelligence. It is the explicit use of an environmental object to alter the animal's physical capability. But even more profound than the tool use itself is the way this technique spreads. This is not a behavior programmed into their DNA. It is a learned, acquired skill. Young female calves closely watch their mothers perform this sponging technique for years, meticulously studying the process, until they master it themselves. The knowledge is actively passed down from generation to generation through observation and teaching. It is not genetics. It is a fundamental, undeniable definition of culture, a specific, localized tradition held and transmitted entirely within a society of marine mammals. As the hunt along the seagrass meadow eventually slows, the exhausted, decimated sardine school finally disperses, leaving only a few scattered survivors fleeing blindly across the bright reef flat. The dolphins regroup, their bellies full, and the intense, disciplined atmosphere of the hunt instantly evaporates. They begin to circle one another, their movements shifting from tactical precision to fluid, exuberant joy. A young dolphin accelerates vertically toward the surface, breaching the water with explosive force, leaping 10 feet into the bright tropical air. It twists its body against the sky before re-entering the water with a massive, percussive splash that sends shockwaves across the calm morning sea. Its companions immediately follow, riding the pressure waves generated by each other's bodies. This playfully chaotic behavior reflects another, deeply compelling dimension of dolphin intelligence that extends far beyond the cold, evolutionary calculus of sheer survival. Dolphins possess a massive capacity for play. They frequently engage in activities that appear to have absolutely no functional purpose other than pure enjoyment. They will relentlessly chase one another through the coral heads. They will carefully balance pieces of seaweed on their pectoral fins and toss them back and forth in a game of underwater catch. They will aggressively seek out the massive, rolling pressure waves created by passing ships or the cresting waves of the surf zone, solely to ride the hydrodynamic energy for the sheer thrill of speed. While play serves critical developmental purposes, strengthening vital social bonds, reinforcing alliances, and providing young calves with a safe environment to practice the complex motor skills they will later need for hunting, it also reveals society capable of experiencing leisure, joy, and emotional release. The depth of their emotional lives is profound and often beautifully tragic. Observations of wild dolphin societies have documented behaviors that point undeniably to a deep capacity for empathy and profound grief. Dolphins maintain incredibly intense, long-term relationships with specific companions, forming political and social alliances that can persist for decades. Mothers invest staggering amounts of physical and emotional energy into raising their calves, nursing them for years while patiently teaching them the incredibly complex rules of their acoustic culture. When illness, injury, or old age strikes a member of the pod, the society does not abandon them. Dolphins have been repeatedly documented physically supporting injured or dying companions, swimming just beneath them to gently lift their heavy bodies to the surface so that they can continue to breathe the vital air. They will stay with a sick pod member for days, aggressively defending them from passing sharks, risking their own starvation and safety to comfort a friend. And when a calf or a bonded companion finally dies, dolphins have been seen carrying the lifeless body through the water for weeks, displaying prolonged, heartbreaking behavior that can only be described by the human concept of mourning. To feel such intense grief, an animal must first possess a profound, conscious understanding of love, attachment, and the concept of loss. The massive, heavily folded brains of the dolphin are equipped with the exact neurological hardware required to process these overwhelming emotional extremes. As the midday currents begin to strengthen and the brilliant tropical sun reaches its absolute zenith, the shallow coastal water begins to heat up. The pod turns its collective attention away from the reef, shifting their formation to move outward toward the deeper, cooler channels of the open ocean. To survive in environments where water temperatures can fluctuate wildly, dolphins rely on a brilliant physiological adaptation known as countercurrent heat exchange. Woven deeply into their circulatory systems, the arteries carrying hot, oxygen-rich blood away from the internal organs are surrounded entirely by a dense network of veins carrying cold blood back from the external flippers and tail. As the hot blood travels outward, it physically transfers its heat directly to the incoming cold blood. This miraculous internal radiator system prevents the dolphin's core body heat from being ruthlessly sucked away by the surrounding ocean, allowing them to conserve massive amounts of metabolic energy while traveling through deep, freezing thermoclines. Gliding effortlessly through the deep blue channel, the dolphins maintain a steady, comforting acoustic contact. Occasional, soft signature whistles ripple through the water column as individuals check in with one another, adjusting their relative positions in the dark. The group remains loosely connected, a beautifully synchronized organism, each member hyper-aware of the others through a seamless, overlapping blend of acoustic signals and invisible echolocation echoes. Within the vast, unforgiving hierarchy of the marine ecosystem, dolphins occupy a position that is entirely unique. They are apex predators, yes, capable of immense physical speed and coordinated violence. But their true dominance is not born of sharp teeth, venom, or impenetrable armor. It is born of the mind. They are the philosophers of the sea. Their intricate hunting strategies shape the very distribution of fish populations, while their nomadic movements link the coastal shallows with the deep, offshore feeding grounds. But it is a staggering intelligence displayed in their acoustic communication, their cultural tool use, and their profound, empathetic social relationships that truly sets them apart. It suggests that these animals perceive the ocean in a way that is vastly, deeply different from the cold, instinctual perception of a shark or a barracuda. They do not just live in the ocean. They understand it. They manipulate it. They experience it. As the afternoon sun casts long, shimmering rays into the deep water, the entire pod angles upward, moving in perfect, flawless unison. They rise toward the ceiling of their world. They break the surface simultaneously, a dozen blowholes opening in the exact same fraction of a second to draw in a massive, synchronized breath of life, before descending smoothly back into the clear, endless blue depths. Beneath the water, their dark silhouettes merge back into a single, fluid formation, moving with shared, conscious intention rather than solitary, blind impulse. In this vast, alien underwater world, evolution has taken countless, bizarre paths to ensure survival. Some creatures rely on perfect invisibility. Some rely on the crushing weight of a shell. Some rely on the pure, terrifying physics of speed. But the dolphin followed the most complex, difficult trajectory of all, the path of the mind. Their presence transforms the ocean. They navigate the darkness not with light, but with a symphony of sound. They survive not through solitary strength, but through the unbreakable bonds of family, culture, and cooperation. As the pod finally disappears into deep, offshore channel, fading entirely into blue shadows where the continental shelf plummets toward the abyss, the water returns to its quiet, indifferent rhythm. Yet the impression left by their passage lingers heavily in the current, a powerful, undeniable reminder that among the billions of life forms fighting for survival beneath the waves, there exists a profound, self-aware intelligence looking back at us from the deep. The ocean floor at first glance is an exercise in profound, unending emptiness. It is a pale, quiet plain, broken only by the occasional scatter of coral rubble or a lonely patch of seagrass swaying helplessly in the slow, rhythmic pull of the coastal current. To a human observer or a passing predator, there is nothing here to command attention. It is a landscape of shadows and stillness. Yet, perfectly hidden within this barren topography, wedged into a space so impossibly tight it defies physical logic, rests one of the most astonishing alien minds evolution has ever produced. Beneath a jagged ledge of dark volcanic rock, an octopus waits. Its soft, entirely boneless body is folded, compressed, and contorted into a narrow crevice. From the outside, it appears as nothing more than a trick of the light, a shifting, ambiguous shadow cast against the rough stone. But inside that compact, resting form exists a neurological architecture unlike anything else on planet Earth. When we think of intelligence, we are biologically biased to imagine a centralized command center, a single brain, locked securely inside a rigid skull, dictating every movement to the passive limbs it controls. The octopus shatters this paradigm entirely. It possesses a massive nervous system containing hundreds of millions of neurons, but the vast majority of these neurons are not located in its head. Instead, they are distributed outward, embedded directly into the thick, muscular flesh of its 8 arms. In a very literal biological sense, the octopus's mind is spread throughout its entire body. It does not simply control its arms. It is a creature composed of 8 semi-independent, thinking extensions of perception and decision-making. It is a decentralized network of intelligence, moving like a fluid, calculating shadow across the seafloor. Slowly, deliberately, the octopus extends a single arm from the absolute safety of its volcanic shelter. The movement is not rushed. It is an act of pure, exploratory curiosity. Along the pale underside of the twisting limb, Hundreds of muscular suction cups probe the surface of the stone. They press against the rock like thousands of highly sensitive, blind fingertips. But these cups do far more than just feel the physical texture of the environment. They possess a sensory superpower. They taste the world. When a suction cup touches the seabed, it instantly analyzes the microscopic chemical landscape. It tastes the invisible film of algae, the presence of bacteria, the faint, lingering metallic tang of the minerals. And then the arm detects something incredibly specific. The rock carries the faint, ghostly chemical scent of crab that scurried past hours earlier. In a human, that sensory data would have to travel all the way up the arm, into the spinal cord, and up into the brain to be processed and acted upon. In the octopus, that information does not need to travel to the central brain at all. Complex, localized neural circuits embedded directly within the arm itself begin processing the chemical data in real time. The arm evaluates the strength of the scent, determines the likely direction of prey, and independently decides that the trail is worth pursuing. The arm begins to creep forward, actively hunting on its own, before the octopus's central brain has even fully engaged with the decision. The creature behaves less like a single, unified dictator giving orders, and more like a brilliant cooperative council of 8 semi-independent explorers, constantly feeding a stream of sensory discoveries back to a central, coordinating mind. As the first arm follows the invisible chemical whispers across the sand, a second arm emerges from the crevice, probing in the exact opposite direction. This decentralized design is evolution's flawless solution to a catastrophic computational problem. Because the octopus entirely lacks a rigid skeleton, it possesses virtually infinite degrees of physical freedom. Every single arm can bend at any point, twist in any direction, elongate, or contract simultaneously. If a single, central brain were forced to consciously calculate the exact physics, angles, and muscular contractions required to move 8 boneless limbs in an infinite number of directions, the computational demand would crash the system. Instead, the central brain simply delegates. It sets a broad general goal, search for food, and the highly intelligent arms figure out the exact physical mechanics required to execute the mission. The result is a creature capable of terrifyingly fluid, improvisational movement through the most chaotic, complex environments the ocean has to offer. The octopus finally glides out from its shelter, fully exposing its soft body to the open water. As it spreads its arms like a living, pulsing net across the sand, its skin begins to undergo a transformation that borders on witchcraft. Just beneath the surface of the animal's epidermis lies a dense, microscopic layering of biological technology. Millions of tiny pigment sacs, known as chromatophores, are wired directly into the nervous system. In milliseconds, these sacs violently expand and contract, flooding the skin with bold flashes of red, brown, yellow, and black. But color alone is not enough to disappear. Lying just beneath the chromatophores are specialized cellular mirrors called iridophores and leucophores. These cells actively manipulate and bounce incoming light, producing shimmering, metallic blues and greens that perfectly mimic the shifting optical properties of the surrounding water and the ambient sunlight. Simultaneously, the physical texture of the octopus's skin radically alters. Bundles of specialized muscles violently contract, pushing the previously smooth skin upward into jagged, three-dimensional bumps and sharp ridges called papillae. In less than 2 seconds, the smooth, pale cephalopod is physically and optically transformed into a rough, jagged, perfectly rendered imitation of an algae-encrusted rock. And the most terrifying aspect of this cloaking device, much of its incredible high-definition transformation is managed locally outside the central brain. Neural circuits within the skin itself help coordinate the shifting patterns, allowing waves of camouflage to ripple across the body like liquid data. Recent, groundbreaking biological research suggests an even more alien reality. The skin of the octopus is laced with specialized light-sensitive proteins called opsins, the exact same proteins found in the retinas of eyes. The octopus's skin can literally sense the ambient light and color of the environment directly. An arm reaching blindly behind a rock can automatically adjust its own camouflage to match the hidden surface it touches, without the animal ever needing to look at it. The entire creature is a distributed, seeing, feeling, adapting optical illusion. Suddenly, a shadow sweeps across the reef. High above in the water column, a massive grouper is patrolling the drop-off, its large eyes scanning the bottom for movement. The octopus freezes instantly. Its skin darkens, the papillae rise sharply, and it becomes a lifeless lump of stone. Predators that rely on visual outlines and the subtle twitch of muscle completely overlook the disguise. This absolute mastery of deception is the brutal tax the octopus must pay for its biology. Having surrendered the heavy, protective shells of its ancient nautilus-like ancestors millions of years ago in exchange for unmatched, boneless mobility, the octopus is left entirely naked in an ocean filled with armor-piercing teeth. It has no bones to stop a bite. It has no spines to inject venom. Its camouflage is not a parlor trick. It is an absolute critical life-or-death defense system in an ecosystem swarming with hungry sharks, moray eels, and apex reef fish. The grouper's shadow fades into the blue. The rock exhales, and the octopus resumes its hunt. One of its searching arms suddenly stiffens. The incredibly sensitive suction cups have encountered a narrow, jagged fissure between two slabs of dead coral. The chemical receptors scream with the overwhelming, unmistakable scent of a hidden crab. The arm slides deep into the dark opening, bending, twisting, and compressing its boneless form to angles that would instantly shatter a vertebrate limb. Deep inside the black cavity, the arm becomes a blind, tactile hunter. The central brain knows the prey is there, but the intricate, violent mechanics of the capture unfold entirely to the localized intelligence of the arm itself. The crab senses the intrusion and attempts to desperately scuttle backward. Deeper into the maze of the reef, the arm adapts with lightning speed, instantly coiling and twisting to block every conceivable escape route. In a flash of coordinated violence, the octopus lunges forward, throwing the weight of its body against the rock. It fires 3 more arms deep into the crevice. The limbs work together like a pack of experienced wolves, predicting the crab's frantic movements, adjusting their grip, and finally locking their suction cups onto hard, chitinous shell. The struggling crab is violently ripped from the safety of its cave and dragged directly into the center of the octopus's webbing. Hidden deep within the convergence of the 8 arms lies the predator's only hard structure, a dark, devastatingly sharp beak. Shaped almost exactly like that of a parrot, the beak effortlessly punctures the crab's thick armor. A highly specialized, toxic saliva floods into the wound. This chemical cocktail contains potent digestive enzymes that immediately begin to paralyze the crab and dissolve its soft internal tissues into a liquid soup, allowing the octopus to effortlessly consume its meal from the inside out. This effortless, calculated predation highlights a level of intelligence that leaves marine biologists astounded. The octopus does not hunt purely by hardwired, unthinking instinct. It demonstrates a staggering, undeniable capacity for complex problem-solving, learning, and adaptability. In controlled laboratory environments, these invertebrates have routinely shattered the expectations of science. They have effortlessly learned to unscrew the lids of sealed glass jars from the inside to secure food. They have navigated complex, multi-stage mazes. They have recognized individual human faces, spraying water at researchers they dislike and greeting those who feed them. They display a level of cognitive flexibility that is almost completely absent in the invertebrate world, rivaling the intelligence of crows, dogs, and some primates. This intelligence was born of vulnerability. When the ancient ancestors of the octopus shed their heavy, protective shells to become fast, agile hunters, they entered an evolutionary arms race. Without physical armor, they faced total annihilation from the fast-evolving, jawed fishes of the ancient seas. To survive, they had to become smarter. They evolved massive, complex nervous systems to pilot their newly liberated, infinitely flexible bodies. As the octopus finishes its meal, it begins to creep across an open, highly exposed patch of sand. The landscape here is totally barren, save for a few scattered, unusual objects. Resting on the sediment are 2 halves of an empty, broken coconut shell, discarded long ago by the coastal tides. The octopus pauses. It does not ignore the debris. It reaches out, its arms carefully, deliberately examining the shells, testing their weight, feeling their concave shape. And then, the octopus does something that fundamentally rewrites our understanding of animal intelligence. It gathers the 2 heavy halves of the coconut shell beneath its body, wrapping its arms tightly around the wooden debris. The octopus lifts itself up and begins to walk across the seafloor. The movement is awkward, physically demanding and entirely unnatural. The creature is literally tiptoeing on the very tips of its arms, awkwardly carrying the heavy shells like a biological pack mule. This is explicit, undeniable use of tools. The octopus continues its clumsy, laborious march across the exposed sand until it reaches a new, highly vulnerable location where it decides to rest. It drops the shells. It carefully, meticulously arranges the two halves around its soft body, perfectly assembling a protective wooden dome, and slips quietly inside. From the outside, there is no octopus. There's only a piece of tropical debris resting silently on the sand. The octopus carried those heavy shells for hundreds of yards, completely exposed, when they offered absolutely no immediate protection. It performed this exhausting task because it possessed the cognitive ability to anticipate a future need. It understood that eventually it would require shelter in an area where none existed, and it planned accordingly. This level of foresight, of carrying a tool for future deployment, is a hallmark of profound, abstract thought. As the deep, oceanic currents shift with the turning of the tide, the octopus eventually abandons its wooden fortress, slipping back out onto the reef to continue its endless, sensory dialogue with the world. Its skin ripples with texture and color, an unbroken, silent conversation with the light, the shadows, and the stone. It is the ultimate evolutionary paradox. Here is an intelligence so vast, so deeply capable of learning, planning, and tool use, yet it is trapped within incredibly fleeting existence. The vast majority of octopus species will live for only a year or two. They have no elders to teach them. They have no society to protect them. They are born as microscopic orphans drifting in the plankton, and within a single brief spark of a lifetime, they must independently figure out the physics of their boneless bodies, master the optical illusions of their skin, and outsmart the greatest predators of the sea. As the sun begins to lower toward the horizon, casting long, dark shadows across the coral, the octopus flows like liquid back into a narrow, jagged crevice. It folds its 8 arms into a tight, defensive spiral. Its skin instantly fades into the exact mottled hues of surrounding rock, rendering the genius of the reef completely, perfectly invisible. But beneath that flawless, quiet disguise, hundreds of millions of neurons continue to fire. The decentralized mind remains awake. In the silent, brutal world beneath the waves, the octopus stands as the ultimate, breathtaking proof that intelligence does not require a skull. It is an animal that does not simply think with a brain, but thinks with its skin, its muscles, and its very existence, a brilliant alien mind spread perfectly throughout a body without bones. The ocean covers more than 70% of our world, yet it remains the ultimate frontier, a boundless, unforgiving theater where evolution, physics, and raw survival collide in the dark. We have only just scratched the surface of the stories hidden beneath the waves. If you want to continue plunging into the unknown and uncovering the deepest, darkest secrets our planet has to offer, make sure to hit the subscribe button and turn on the notification bell so you never miss an expedition here on Earth's Documentary. Leave a like if this journey changed how you see the natural world, and tell us in the comments below, which of these evolutionary marvels terrified or fascinated you the most? The wild is always waiting. We'll see you in the next exploration on Earth's Documentary.